All right, we'll probably get started there. Welcome everybody to the compensation workshop. What we're going to try and tackle today principally is looking at how to, look at our flow cytometry data after we've performed things like compensation or unmixing, how to assess how well that's gone, and if necessary, how to adjust our compensation results in a way that is kind of methodical and robust, which is important. So what I'll do to start off with is we'll talk through a little bit of the principles about how compensation works, what things like spreading error are, and what are the common causes of error in compensation. We're going to apply this to some spectral unmixing as well at the end, but we're going to start with kind of conventional compensation to get to grips with the fundamentals, and then we'll sort of apply that in a slightly different way using unmixing. So to begin with, what we're talking about here in this context is really about the fact that we're measuring things about cells using fluorescence. So we put a fluorophore on an antibody and we label an antibody, and we label a cell with that antibody. We can measure the amount of light coming essentially off the cell when we pass it through a laser, and that light corresponds to how much of that, let's say, that protein is on the cell. This in flow cytometry is kind of the fundamental thing that we rely on. So we're sort of using light as a surrogate for level of protein expression. In two fundamental ways, we can get problems here. The problem comes from a degree of overlap. So if we, for instance, have two fluorescent molecules that we've put on a cell via an antibody, let's say in this case PE or phycoerythrin and PECF594, which is a tandem of PE. These are two fluorophores which are both excited highly by a yellow-green laser, 561 nanometers. So this is very good. We can have these two fluorophores on a cell. We can excite them with a yellow-green laser, and we can get some signal coming off them. But if you see here, there is in fact overlap between those two signals. If we look at this sort of brown, yellow, orange, brown curve, this is the emission spectra for PE. So if this one on the left is the excitation spectra, we sort of get to see whereabouts this fluorophore is most heavily excited. In this panel here, we get to see where it emits. And so you can see here in terms of the wavelength, there's a maximum emission for PE around 580 nanometers. And so we can use an optical filter to collect that light in the system. But what you'll notice is that in the next detector down, different filter settings, we have a certain level of spillover. This is like contaminating the detector next to it. And this detector is the one that we want to pick up this blue signal, which is the PECF594. So these are neighboring fluorophores. They emit very close together and they spill into each other's optical detectors on the machine. And so this is kind of the fundamental problem that we have to deal with. We're getting false positive contaminating signals is the easiest way to think about that. Now, what happens here is that this is one laser, which is kind of exciting both fluorophores optimally, and they emit in kind of areas that are near each other. We can have a similar situation where we're getting a laser that excites two fluorophores that are, it's not the same. This is not exciting PE-Cy5 optimally. It's at about 30% of what would be optimal. And it's exciting APC really quite strongly. But the emission properties of both of these molecules are very much the same. So even though we're not getting optimal excitation of PE-Cy5, it's still going to show up in the same detector that we would detect APC, even though we kind of think of them as belonging to different lasers. We're going to excite normally the PE-Cy5 using the yellow-green laser and APC using red, but the red is going to excite the PE-Cy5 whether we like it or not. And so we're going to get this cross-laser spillover in this case. I think, the way we try to design these is we think about all these kind of fluorophores and their emission being separate, but in reality, they're actually highly overlapping. And so this is kind of the fundamental problem that we have to deal with in working in flow cytometry. The problem is similar in spectral cytometry, but the actual specifics of this are a little bit different, and we'll come back and deal with that a little bit later on. So the way that we deal with this is we kind of address the problem computationally. So we actually ask the computer to help us out. So in this example here, what you can see is what the data looks like uncompensated, so raw. We haven't made any changes yet. So each dot on here, I realize this is kind of a line, but it's actually a series of dots, and each dot represents a cell, well, sorry, a bead in this case, not a cell, and they are labeled with PE, phycoerythrin. And so they should only be showing up in the PE detector, in theory, and not in another detector. But because we have this spillover event, the PE signal is going to show up in its own detector, but also the neighboring detector, we can see that it looks double positive. It looks like it's showing up in both detectors. So this is the problem of spillover. If it's showing up in one detector, it's going to show up in another detector to a certain amount. Now, the actual math behind how we might correct this is a little bit more complicated than what I'm going to describe here, but fundamentally what we can do here in terms of the user input is we can say, okay, what percentage is this spilling over, relative to how strong it is in its primary detector, and then we can correct the signal by that factor. So if we assume that, okay, so it's at around 40,000 here in its primary detector, and it's at around 6,000, almost 7,000 here, this is going to be a ratio of about 16% or about 17%. So this is, in this case, we'd call this a compensation value. Now, if these beads were kind of, at 40,000 in its own detector and 40,000 in another detector, we would call that 100%. And that's, I only raise that because I just want to point out that this is just a mathematical ratio. The higher the number doesn't necessarily mean the worse the spillover. Kind of, I suppose, the way we interpret it, we tend to look at the higher the number being the worse the problem. It's not actually as straightforward as that. We'll come back to that as we explore a few examples later. But what I just want to hammer home here is that the value is simply a ratio from where it is in its own detector to where it is in another detector. So if we apply a compensation matrix and the value that we're applying to these pair of detectors, we can correct the signal. So if we apply a small amount of compensation, then this signal actually starts to get moved out of the non-target detector on the x-axis, whilst keeping its position in its primary detector on the y-axis. So 2%, it's kind of moved a bit to the left. 10%, it's moved a bit further. 16.9%, it's kind of been corrected. It's been taken from spilling over, appearing in both detectors, and it's been removed from the non-target detector. And that's where it ends up there. And then, of course, actually, if we keep increasing this value, we see, we see that this will keep, oh no, it's all coming apart. If we increase this value, we can see that this actually goes further and further and starts to become, in this case, we would call this overcompensated, which is also a problem. So this is something that we have to tackle and something which is really important. So what we're going to do is basically do this for all pairs of fluorophores that we have in our system. So if we've got an 18 color panel, we'll be comparing 18 colors versus 18 colors and creating a matrix which will calculate these factors for us. Back in the day of kind of 2-color flow, this process would be done manually. But fortunately, if we record single stain controls, we can have the computer calculate this for us, which is very helpful. Importantly, there's a factor here which we haven't kind of addressed specifically yet, which is that if we look at this correctly compensated data here, we can see that this isn't actually as straightforward as I'm making it out to be. This red population is kind of spread out compared to the negative control down here. So it looks corrected in that it's no longer sort of appearing in the non-target detector, but something's still not right. So this is correctly compensated, but what we're observing here is a phenomenon we call spreading error. And we'll come to that in just a second, in the next couple of slides. So these are the fundamental premise, the fundamental premise we need to deal with when we're going to go and make assessments about our compensation, how well it's worked, and then how we're going to deal with it if it hasn't worked. We're getting spillover of signal between multiple detectors, and we're applying some correction factor to try and adjust how that data looks. Now, spreading error is worth talking about here because this is kind of the, one of the factors that we're going to come to as we start troubleshooting through data. Spreading error is, it's a weird thing to kind of appreciate, but it's essentially, it's a facet of physics in this case. When we measure photons that are coming off, a fluorophore from a cell, there's a certain amount of error in the way that we measure it. So like measuring anything, right? Even microliters from a pipette, there is the kind of the true value which we're trying to get, but the actual value you get may be plus minus the true value by a certain amount. So there's error in everything, and this is just inherent to the world that we live in. And the same is true for the way we count photons. So let's say, I don't know, there's 1,000 photons exactly coming off a fluorophore. When we measure that on any given time, maybe it's 900, maybe it's 1,100. So we're getting error that we can't control for. The way this shows up in flow cytometry data is if we have a look at this left panel in E here, we have P and P's F594, just like before. If we look at the uncompensated data, we can see that as the signal is getting brighter, and remember this is on a bi-exponential scale, so all of this section here is in log. as this signal is getting brighter and brighter and brighter, there's actually a bit of width to this. It's a bit hard to really appreciate at a low level, but for every measurement, there's a little bit of wiggle room on the x-axis. When we compensate it, you can see that this actually creates some spread here. Now, importantly, this spread is not generated by compensation, it's simply revealed by compensation. The measurement error here, this spread, is already inherent to the data. So it's already there, we can't do anything about it. All compensation is doing is revealing it by sort of moving all of this data down to the lower end of this bi-exponential scale. Oops. A better example of demonstrating this is probably in this case. So if we're comparing P with, in this case, PV570, we can see that this width of this uncompensated signal is actually much wider than in the example on the left. And when we compensate it, as we can see, the spread is also much wider. This is a problem. This is kind of going to create some issues for us in the way that we analyze our data. But importantly, this is not something that we can correct. This isn't sort of data that we've kind of overcompensated or undercompensated. This is just physics. This is something we can't change. The only way we can change it is by going back and adjusting our panel. And we'll see a few examples of this shortly. I mean, why is spreading error important? Two cases down here that sort of paint a picture of when it's irritating but not necessarily a problem versus when it's actually going to mess with the experiment. In this case, if we imagine fluorophore A versus fluorophore B, fluorophore A, as we're getting brighter, the signal starts to spread, and so it starts to kind of contaminate our fluorophore B detector. If we then look at cells that are kind of positive for both A and B, in this case, we can pretty much resolve them. They do still separate. So you can see the single positives in blue and green and the double positives in red. So actually, this doesn't look too bad. We can probably deal with this problem without it causing us too much of a headache. However, if we look at this example on the right, this is slightly different. This is where we're seeing overlap. In this case, the single positive here in blue and the double positive here in red are actually overlapping. So we can't draw an accurate gate that will allow us to see the red cells separately from the blue cells. So if you imagine this could be, let's say, fluorophore A is kind of labeling a T cell marker, CD3, maybe B is labeling some kind of activation marker. In this case, what we wouldn't be able to do is we wouldn't be able to see how many T cells have become activated because the actual CD3 signal is going to prevent us from doing that. And this is where spreading error becomes a pretty significant problem. Now, there are ways of dealing with this in terms of panel design, and those we're not going to get into specifically today. What we're going to do is learn how to identify these patterns and learn whether it's just a simple spreading error artifact or whether it's actually an error in compensation that we've made, which we might want to go and tackle. Now, what I'm going to discuss briefly here is some practices that can help us avoid problems with compensation. The idea here is that prevention is always better than cure. So if we can prevent these problems coming up, then there's nothing to correct. Typically, this is true for most situations. Even our larger panels, I think there's often this idea that big panels, you're always going to have to correct compensation, and that's not actually true. With kind of rigorous controls and practices, you can have compensation that works reproducibly every time, which is an important thing to kind of stick to. Like doing the upfront work properly really does help. And so this stuff is important, and we're going to just address it briefly. These are four rules that we've kind of put together, which, well, not we, I guess the field has kind of consolidated on, which will give you the best, or is it the highest likelihood of having good compensation. So, I mean, there's a couple of aspects that we need for this. If you're going to have a sample that's labeled with multiple fluorophores, so, different fluorophores that will label CD3, CD4, CD8, etc., you need to have a set of single stain controls that consist of only one color each. So you need to have a single stain control, which represents PE, one which represents whatever the other colors are, FITC, APC, etc., etc. If you have 18 colors in your panel, then you need 18 single stain controls. This is very important. One aspect which is, I suppose, convenient is that you can do this using either cells or antibody capture beads. And this just provides a lot of flexibility. Using cells is often like a good way to go, but not always, and we'll come to that at the next point. But antibody capture beads are very popular, and I think people really appreciate using them because they will bind to, depending on which one you buy, whichever antibody that you've added. So it's not antigen specific, it'll bind to the antibody itself. So this is very helpful. Fundamentally, the issue here that we need to have is we need to have a strong positive signal and a strong negative signal. This is kind of what we want to be able to see. So if, for instance, you've got a fluorophore which you're going to use to label something that's very lowly expressed, let's say something like CCR2, a chemokine receptor, on cells, that's actually going to be very lowly expressed, not far above background. Cells in this case may not be a good single stain because you won't get a solid positive peak, which means you can actually separate positive from negative. And we actually really need that. If we start gating, if we start trying to make like a little, okay, well that bit's probably positive, above background. If we're capturing some of our unstained cells in there, we actually run into a lot of problems. And we'll come back to that in a minute. So we need to have positive that separates from negative. And so if we don't have that on our cells, then it's a good idea to use beads, because beads will give us a strong positive signal and a low unstained signal. Importantly, the positive signal needs to be either as bright or brighter than what's on the fully stained sample. The idea here being that what we're essentially doing is teaching the computer to identify how much compensation it needs to apply to correct that signal. If what we're giving it to learn how much it needs to apply is not as bright as what's in the actual sample, it might get it wrong. It will do it accurately for what you've given it, but if the real sample has kind of got signal that's much higher, it may actually get that wrong. And we'll see what that looks like using some live analysis in a few minutes' time. But that's very important. Excuse me. Typically, I have a preference if we're using beads to have the negative and the positive beads in the same tube. I think it just makes kind of life a little bit easier. And there's a particular reason this can be helpful, which we'll come to in a slide or two's time. Now, this one's really important and is often missed. The material for the positive and negative events, whether they be beads or cells, the material has to be both for any individual color. So let's say for FITSI, you want to use beads, and for PE, you want to use cells. Totally fine. There's absolutely nothing wrong with doing that. However, if you're going to use beads for FITSI, then both the positive and the negative must be beads. And for the PE, both the positive and the negative must be cells. You can't use positive beads and negative cells, or vice versa. Mismatching the actual material will create some problems, which we'll come to in just a moment. But that's a very important thing to remember. So if we're going to include something like a live dead control, often it's easier to use some cells, including some dead cells, for the single stain control. Absolutely fine to do that, but they must be cells, both the positive signal and the negative signal. So again, you can have a mixture of beads and cells for different colors, but within each color, it must be the same. That's very important. And the fourth thing, and this is, I suspect, probably the most common thing which leads to compensation issues, is that the way you treat the single stain controls must be the same as the way you treat the samples. This, I think, is probably the big one, is if you fix samples, which is very common, particularly for people working on human cells, instinctively you're like, well, I mean, if I'm using compensation beads, I don't need to fix them. There's no possibility of having pathogen in amongst compensation beads, whereas in my sample, if it's human blood, it is possible. And so instinctively, it's like, well, I mean, why would I fix my beads? Fixation actually does change the fluorescence of these fluorophores. And so in theory, if you fix your samples, but you don't fix your single stain controls, your single stain controls no longer match what's in the sample. So it'd be equivalent of using, Percy P as a single stain to try and control for Percy P side 5.5. Like it's close, but it's not the same. And this is really important. Fixation makes a big difference, and we need to kind of accommodate that with what we're doing. This also applies to other things, like if we're using permeabilization buffers of different sorts. Wow. I don't know if you guys could hear that. There's a huge thunderclap right outside the apartment. Where was I going with this? Yeah, fixation. So fixation is important, but also if we're using things like permeabilization buffers, that's actually really important because that can have effects on fluorescence. And so that's something we need to be able to correct for. So that's important. The way we treat our single stains must be the same as the way we treat our samples. So those are kind of the main aspects which I think lead to most compensation errors, and doing these practices will, in the vast majority of cases, prevent any issues that might come up. Now, just to provide an example on one of those points, I talked before about the positive and the negative has to be the same material. There's this one particular issue that comes up every now and then, which is worth people being aware of, This is not work from us. This is some data which was generated at Mass General in the States. If you're using things like compensation beads, some companies sell, it's a tube with positive and negative beads in the same dropper bottle. Some companies sell them with negative and positive beads in separate bottles. The actual batch of the beads generated needs to be the same. This seems a little bit weird. You're like, well, why would it matter if the negative beads are made in a different batch of plastic from the positive beads? The reason for this is that the actual autofluorescence of the beads can change. And this matters a lot because if you have a look here, it's my little annotate button. There it is. These beads in this case are labeled with APC. These are the negative beads. Now, what you can see here is that they are spilling, quote unquote, into the Pacific blue channel. Now, this is actually not true. These beads are actually, this APC signal is actually not spilling into Pacific blue. The autofluorescence of these beads is higher in this sort of violet region channel, about 440 nanometers. And so this isn't actually showing us that APC is spilling over. This is actually just the beads are higher in that channel natively. So what the computer is going to interpret this is like, well, APC is spilling into Pacific blue and it's going to correct it, which in the real sample is going to, create some errors because what's going on here does not represent what's actually happening in the sample. And so this is one of these weird little, it's a really specific problem to have, but it actually does create errors, and particularly in the sort of the violet region of the spectrum. And as a result, it's very important to tackle this properly, so these issues don't come up. So if you, for instance, if you get your sort of positive and negative beads and you check that they're from the same batch, that's a really good practice to instill. If you're using beads like the ultracomp beads that are sold by Fmo, they just contain positives and negatives in the same tube, and so there's nothing to check. But always worth keeping in mind because that can lead to headaches without kind of really understanding why. Excuse me. This is kind of just the I suppose the what do you call it? The end product of using this kind of mismatched bead situation is you end up with compensation errors where there shouldn't have been any in the first place. So that's worth keeping in mind. It's fairly uncommon, but it's definitely worth being aware of. All right, so the way that we calculate compensation, we're going to do live, and we're going to essentially just look at what a compensation matrix looks like. So we're not going to kind of manually go and create all the compensation values, but we are going to go through and look at what the result, the final product looks like and how we might adjust it if we need to. Just because we're going to try and do this interactively, please feel free to unmute and ask questions or object to certain practices or make comments. That's totally fine. We can just do that kind of as we go. So just before we kind of move on, does anyone have any questions about some of that content that I just shared?
Thomas?
Yep, go ahead.
One extra sort of rule I try and tell users is to collect enough positive events, because sometimes I see people trying to do compensation with 127 events in the positive gate.
Yeah.
And, people have to remember it's a statistical method that it's using. So obviously collect enough events. I don't know what your views on numbers are. I would say at least 500, try and get 5,000. If you read some of Mario stuff, he says 50,000, but like 57 or 100 events probably isn't going to give you a great comp matrix.
That's a really good point. I'm glad you raised it. I hadn't thought to mention that, so thank you. Yeah, I have been tending to tell people to aim for like 10,000 positives and 10,000 negatives, not because that is the magic number, but just because they've then got signal in abundance, which I don't know, sometimes for whatever reason in one particular sample, you've got your positives are much lower than the negatives for some reason, ratio wise, and so you end up with less than you thought. So I've been kind of doing that as collect 20,000 total to end up with hopefully 10,000 each. And then if you're slightly wrong, then it's well, you're kind of protected. So that's a really good point. Thank you for raising it.
Can I add on to that as well? Also, if in the situations where you get less, say you try to aim for 10K recording or 5K recording positives, but you end up with something like 100 or 500, then don't extend or expand your gate to try and get some of the lower ones, thinking that you're going to get flat numbers. This is something that I've seen before as well in some of the users who are doing comms, and it can lead to like what Thomas is saying. You added in some actual negatives, and then that's going to cause a lot of issues as well.
Yeah, I totally feel I have those moments. I'm like, if I just drag it a little bit further, I'll have enough events. But yeah, as you say, if you start capturing particularly negative events inside the positive gate, it all starts to go a bit bad. So definitely. I should also just mention on the topic that so those rules in general apply for spectral cytometry as well. For the most part, there are a few differences with how the spectral and mixing process is done, a few like additional requirements which are different, and we will talk about a little bit of that, but the fundamentals of those things that we just discussed are the same. So like the things need to be treated the same as the way your samples are, etc. So from that point of view, the fundamentals are apply to both. There's just some additional aspects with spectral, which we'll come to a little bit later on. Cool. All right, well, we'll press on with some examples. So what I've got up here is some data from recorded from an X20, and I've kind of pre-set up a few like compensation troubleshooting, I don't know, classics, as it were. And I'm gonna just share a preview of what they are. Part of me thinks I should not show the preview and we just work it out on the way, but I do think it's important to kind of have an understanding of what we're trying to tackle. Let's make sure the screen's there. Good. Oh, it's not. No, it doesn't matter. What we're going to look at is three principal problems, and kind of in different ways they might manifest. So there's three here, and so there's C, D, and E. The first is undercompensation. So this is essentially where we've got that kind of leaning population where, you know, before the objective was to move this to the right. In this case, it hasn't been corrected. So this is almost like it hasn't had any compensation applied. Typically, you know, the way this would manifest is like, it's not like no compensation has been applied. It's more like there hasn't been enough of a compensation value applied. So we call this undercompensation because it hasn't been sufficiently moved to the left. And so this is the corrected version where the median of the positive, okay, my line is a bit rubbish here, but roughly the median of the positive should line up with the median of the negative. The second situation we'll come across is overcompensation, which is, I mean, as you would imagine, is the opposite problem. The signal has been moved too far out of the non-target detector. In this example, the way we might come across this might be something like this. Essentially, if we're looking at where the 0 is here, which is kind of where this dotted line is, we're seeing these events which we'd call like super negative. They're kind of way, way below the 0. And this is, you know, this is a red flag. This is like, okay, there's something going on here that we need to deal with. But it's not actually, oh, I just realized that that's the fluorophore and I've written the antigen there. Ah, damn. That's actually in a published paper. I'm surprised that hasn't been flagged somehow during review. Anyway, it's fine. Whatever. So this was BB421 from memory. So it's not actually BB421 versus BUV737. That's not where the problem is. It's not taking BB421 out of BUV737. This is just the way that we've seen it. If we switch from BB421 to BUV395, then we actually see a pattern that makes sense. We actually say, okay, it looks like it's BUV395. That as it's getting higher, it's kind of, you know, leaning left or right. And so this is where it gets a little bit complicated. Undercompensation, it's easy to miss because you're not necessarily going to see this pattern if you're just looking around in your data. Whereas in this case, you may see it in multiple channels, but you don't know what the offending fluorophore is. If we saw this with BB421, BB421 isn't the bad guy. It just happens to be the plot which showed, you know, these guys were all super negative. The reason for this is, you know, if this x-axis is the same in both cases, then these cells are still going to be in their same place on the x-axis. They're not going to move. They're just going to move on the y-axis. So we'll always see the super negative regardless of what we're putting on the y-axis. So there's a bit of a patternistic kind of mechanistic approach we can take to figure that out. So they're the first two. So undercompensation and overcompensation are kind of the classics. These are errors in compensation that we can go and do something about, potentially. The last one is spreading error. Now, the way we might come across this is something similar with there's this super negative, set of events down here, and it doesn't look like BV605 is the culprit. It looks like, that's just the plot we come across it in. If we change to APC, okay, that looks like APC is probably the culprit. This is not over or under compensation. This is spreading error, and this we can't do anything about. This is essentially that problem that we talked about. Fundamentally, as the signal is getting brighter, it's spreading out like this. This is just revealing the measurement error that's inherent to our data. This isn't caused by compensation, it's just revealed by compensation. And importantly, there's nothing we can do about that. There's no kind of mathematical corrections we can apply to this, which will correct the situation. The only way we can correct this situation is by going back to our panel design and rethinking what we're trying to do. So that's very important. That's a situation which we can't fix, but we can at least identify, which is important for us. This may not necessarily affect my assay, but that is a lot of spread, and I would probably rather not have that, have that in my life if I had the option. So fundamentally, those are the problems we're going to tackle. We'll have a look at what that looks like in real time. All right. So what I've got here is some data and a workspace, and hopefully, so I'll update in just a second for everybody. Hopefully the resolution of this will be good enough to see. And my plot's going to open up somewhere. Yeah. So everyone's seeing, it should be up in just a minute. I think the screen sharing's probably got a little lag time, so I'll just let it catch up. Actually, you know what? Why don't we just try doing new share? Might make things a bit more efficient. Great, better. Okay, so this is a set of mouse bone marrow data that we collected using, in this case, we split the samples and did half of them using our Fortessa X20 and half using our Aurora spectral cytometer. So what I've done is I've set up a few classic cases of kind of over or under compensation and spreading error, and we're going to kind of go and have a little exploration to figure out what's going on in the data set. So what we're going to look at first is an example of, I'm going to call correct compensation, just because good to start with kind of what it should look like, and then we'll kind of mess with things. All right, so if you're using Flojo, the way that you can access the compensation matrix is by clicking on this little rectangular grid here, which will be either gray if it's the default applied on a cytometer, or it'll be colored if you've kind of made one on your own. Now, the way to read this, and hopefully the resolution is okay here for everybody, but essentially the layout's always the same. So in this case, there's each row represents a fluorophore detector pair, and then the column represents the same. And so the way that I like to read this is the row is the contributor. So the row is the fluorophore, and the column is the receiving detector. And just to kind of orient the way this looks, wow. Is you can sort of think of it like the row is on the left, so that's the the y-axis in this case, and the column is the x. So let's have a look at this. This is BV785, so we'll go and find that one here. So this row, oops, oh no, come back. BV785 and spilling into the V610 detector, which is here. So this is the compensation value for BV75 being compensated out of the BV605 detector. That's what we're looking at here. Now, the value is much the same as we talked about before. The actual value here, in case you can't read it, is 0.0781. So it's a very low compensation value. So it's effectively 0. Just to give you an idea of what happens here, if I set this to 0, I mean, it's probably not going to move very much, but it might move a tiny bit. Yeah, it's pretty much no movement. If I turn this up much higher, it's going to push this population that's kind of going up and down. It's going to push it to the left. In terms of the value being applied, it's trying to remove it from the non-target detector, just like that. So that's clearly an example where the compensation has gone too far. It's been too excessively extracted from the non-target detector. Maybe just I'll make it a tiny bit lower just to make it a bit more interpretable. So that's the classic curve that we're trying to look for. There's a couple of situations we'll come to where it's not always clear which is the offending fluorophore. It may not always be easy to interpret. So what I'm kind of trying to just show you here is the pattern, the type of curve that you see here is usually very indicative about which fluorophore is causing the problem. The first step is in identifying the issue. The second step is then how we kind of methodically go about making corrections if we need to. And I'll make a bit of a comment on that in a second. But the first step is just identifying where there's a problem, and this is the type of pattern that we're looking for. One thing which people might actually have spotted already is there's a couple of spots here which have negative values. I was saying that this is like a correct matrix, and I actually take that back. The fact that there are negatives here suggests that I have messed something up along the way. This is an old data set I went back to, so potentially this wasn't perfect, but you shouldn't have negative compensation values. Sometimes just with the kind of the mathematical error that can occur, you can get very small negative numbers that are very near zero. So they're probably just minor errors. If you're getting kind of negative whole numbers, negative 2, 3, 4, 10, whatever, then something has gone wrong. Essentially, you can't have negative compensation, or you shouldn't have negative compensation. If you do, then something has kind of become unstuck somewhere. But just to give you an idea of what happens, if we make it negative, this is going to go in the opposite direction. It's actually going to move it to the right. We shouldn't be seeing anything like that with a negative number, so keep an eye out for that as well. But I'm going to reset this to, what did I say, 0.0781. Cool, so back where we started. So for each pair of fluorophore detector sets, we have a place in this matrix and a value which is applied. Now, the astute of you will see that actually a couple of these values are above 100. I just want to make a very quick point about that as we're sort of tackling this, is that number actually doesn't have to be as scary as it sounds. The number, as we discussed, is simply a ratio from, I guess, the primary detector to the secondary detector for that particular fluorophore. In most panels, you shouldn't be expecting to see compensation values of 100 or above. It depends on the exact fluorophores you're using, how much overlap they have, the individual detector settings. But for reasons we don't necessarily have the time to get into, you can have compensation values of 100 or above, and that can be totally okay. I will say though, unless you're doing very large panels, it's unusual to come across compensation values that are kind of 100 or above. Normally that happens when you're kind of really packing in fluorophores into the spectrum and you're sort of running out of room. So it is worth considering it to be like a bit of a red flag, like it tells you that, hey, maybe something's wrong here. But particularly in large panels, you can absolutely have compensation values above 100, and that can be okay. We'll have a little bit of time towards the end of the workshop where we can look at that in more detail if people are interested. But I think what I would say for now is that if it's kind of an average size panel, it's probably worth considering it to be a little flag that you should go check. But there's nothing wrong with having a value above 100. All right, so let's dive into one of our cases. I've got my notes here so I can remember what the pairs are. So what I've done is, I sort of fabricated it, right? I've created, deliberately entered some compensation errors. So we're going to apply a few of those errors, go hunting, see what we can find, and then follow a method which we can use to help us understand, can we correct it and can we do it reliably? And to do that, so I've just got this compensation matrix here. I'm going to drag it and apply it to the samples. In this case, it's actually important to apply it to all samples, and for reasons which we'll come to in a minute. Before I get stuck into dealing with the messy, uncorrected data, are there any brief questions or comments anyone would like to make at this stage? Cool. All right, we'll crack on. All right, so let's open up some data, have a look around. Now, there's one option that you can use to find where there might be compensation errors is to use this tool down here, the N by N matrix. This is quite helpful, but I must admit I find often not really what I need, but it's definitely of value nonetheless. So what we can do here, for instance, is if we've selected a matrix, we can choose a sample and a population. So let's say our cells. And then we can look at, in this case, the blue is the uncompensated. And if I turn that off, underneath it, the black is the compensated. So this is basically a matrix of every fluorophore, every sort of detector pair. And we can basically explore each of these combinations and go hunting for where there looks like there might be problems. Now, the problems are that kind of that leaning that we were talking about before, that sort of classic curve. So this, what we're going to find here is there are going to be some problems, because I know there are problems because I made problems. There will be some areas which we might flag early on, and then we discover actually that's totally fine, or it's spreading error, we can't do anything about it. So we'll kind of go hunting and see what we come across. Just out of curiosity, I don't know how good the resolution is for those watching, so you might not be able to see it, but is there any spot on the screen? I'm sure you won't be able to read the text, but is there any spot on the screen that someone can see some errors or some potential errors that we might want to tackle? So this is probably a bit of a redundant question because you have no way of actually telling me where those issues are.
I was going to say the second column along, there seems to be an that one, there seems to be what looks like some
down there
overcompensate. No, on the pretty much just sort of like a negative happening in that. Sorry, the first channel. If you go back to the first, can you move your thing?
Actually, yeah, let me I got it. So tell me where to move the little pencil, and I'll put it in the right place.
No, can you move the whole plot to the right, just so we can?
Oh, I'm sorry. I see what you mean.
First channel. So I'm guessing that's going to show it. You can see some super negatives in that first.
Got it. Yeah. Well spotted. So that stuff there.
Yeah.
Yeah. Cool. And because people won't be able to see the numbers, but just so you understand, because it's a half matrix, because like having, the full matrix will include FTSE versus PE and PE versus FTSE, which is the same thing. So it just does the half matrix, but essentially this x-axis at the moment is the Percy Psi 5.5 detector, and that kind of switches over here to the y-axis. So it's kind of like, this is FTSE versus PE, Percy Psi 5.5. This is APC versus Percy Psi 5.5. AF700, et cetera, et cetera. It gets a bit weird to like do the mental geometry to flip the plot, because you kind of go from here to here. But anyway, it's just a thing to point out. Yeah, there's absolutely some super negatives here, and because this x-axis now becomes the y-axis here, you can actually see it occurring in multiple detectors. So very well spotted, and that indeed becomes a problem which we'll tackle. This one is kind of interesting, because this in a way looks like this is actually leaning, right? Let me just clean this up a little bit. As it's getting positive, it's kind of leaning over to the right. This one we'll investigate as well, so we'll sort of put that on the red flag list. Any others anyone can spot?
Yes. Hello.
Hi there.
I saw in the second row on the right, pardon, and on the last two plots, overcompensation.
Yeah, definitely. Yeah, let me get rid of my squirrels. Yeah, and what we'll have a look at here is that this is going to be the same, in fact, the same problem, and it's just showing up in multiple places. Very well spotted. That's probably the most obvious one, where it's like, yeah, okay, that looks like a pretty serious issue. Cool. That is, I think, my notes are right. That is, in fact, the issue for this panel. No, actually, I'm going to give too much away. I'm going to withhold that information temporarily. All right. So in this case, I'm going to open up. I set this up earlier, so I kind of know what the problems are. Oops, I went too far. All right. So Percy P Psi 5.5. Damn, I should have done this from like going from a naive position. So that first one that we brought up was in this case FTSE versus Percy P Psi 5.5, which is this one. So yeah, it's this stuff down here, the super negatives that we're trying to deal with in this case. So what we're looking for is some combination of fluorophore detector that kind of gives us that classic curve, which suggests to us that it's a mathematical, I guess, phenomena, not just something being expressed lower. So FTSE and Percy P Psi 5.5 don't tend to spill into each other very much, and so it's unlikely to be that pair. It's most likely what we're going to be looking for a fluorophore that spills heavily into Percy P Psi 5.5. It's not a guarantee, but the thinking is, I guess, the more spillover you have, the more compensation you need to apply, the more chance there is to get it wrong. If you're simply not applying compensation, then like there is no chance of error. If you're, if the physical application is 0, then you can't have an error in that application. That's not always the case. Sometimes you can have, like in this case, Fitzy could have been the culprit, and for some reason it decided it needed compensation of 10 when actually it needed nothing. But typically, I think the problems come when you get heavy overlap. So if I look down this list, I have a couple of options. Per CP Psi 5.5 is going to pick up quite a bit of spillover from 2 fluorophores in particular, APC and PE Psi 5, as well as a couple on the violet. But I can make a reasonable assumption that if I go hunting, let's say PE Psi 5, I'm going to assume that that's going to be my culprit. I'm just going to check that first. So I'm close. Actually, I'm going to just extend this out a little bit to make it easier to view. Cool. So I'm close, right? I've got this looks like it's leaning to the left, right? So it's like, okay, I'm on the right path, but actually there's this whole positive group up here, and that's not leaning. So this isn't like a mathematical curving of the data as it gets brighter. Something is kind of still weird here. So as much as that would have been my classic go-to to blame PE Psi 5 in this case, because I blame PE Psi 5 for everything, that's not the case here, which is going to drive me mad. So I can use this end by end to kind of help me figure out where the issues are. And I mean, I'm just going to kind of jump to it a little bit because I know where I'm looking. If I go to PE Psi 5, PE Psi 7 in this case, then I think I've kind of found it. I found that actually, okay, as this is getting brighter, it's leaning over to the left. This is my big clue. It's like, okay, that looks like a mathematical correction that I need to apply. So good, that's a good start. There is actually another detector which is going to have issues as well, which we'll see in just a moment if I open it up. So ironically, PE Psi 7 is causing problems in the PERSIPI Psi 5.5 detector, but it's not only that detector, it's actually also in PE Psi 5. So these are 2 separate problems in this example, which are occurring in this case independently. So we're just going to deal with one at a time. It's definitely easier to deal with things in kind of a methodical, process one at a time. Otherwise, it's very easy to get lost. So this is our problem at the moment: the contribution of PE Psi 7 into the PERSIPI Psi 5.5 detector. So this looks like overcompensation. Now, what I'm going to do here to do this in a way that is robust is I'm not going to just start like freewheeling, changing the values here. I'm actually going to bring up a few of my controls and use that to inform me what's going on. Now, the 2 main ones that I need in this case to really help me is a single stain and my FMO. Or FMOs. Now, if you've got like if this is like during panel optimization and you've got all of the FMOs here, then you're in a really good place. If this is kind of a bit more down the track where you don't necessarily have all of them, it can be much more difficult. But I mean, typically these issues get sorted out during panel optimization and during testing. So that way, in an ongoing fashion, you don't need to be kind of, trying to fix these things all the time. Like we said, if we fix these fundamental practices early on, we tend to avoid most of these issues. So in this case, I've got PE Psi 7 versus PERSIPI Psi 5.5. So I want to get FMO controls for both of those colors, which I'll go and do. PE Psi 7. And PERSIPI Psi 5.5. I'm just going to go for the, I've obviously done some prior gating here. So I'm just going to go for the live CD45 cells in this case. Oh, oops, I selected the live gate. This is the issue with doing this in multiple screens. So we're so naive, like, no, multiple screens will be fine. It won't be a hassle at all. Okay, there we go. Now, the FMO controls, in case anyone is not familiar with the term and is like, the heck are you talking about? In this case, an FMO control is essentially the same as the fully stained sample, but one fluorophore has been removed. And so the idea is that if you have a full set of FMO controls, then you have basically as many FMOs as you have colors, -1. So for example, this FMO is the same sample. It has all of the antibodies included except for PESI7. So there is no PESI7 signal in this sample. And this one is for PESI 5.5. So it's the exact same deal, but every color is there except for PESI 5.5. Okay, so, oh, actually, that's interesting. They look slightly different. That's not good. Yes, okay. That's fine. We'll work with it anyway. What we're going to try and do with these FMOs, I actually realized this is the experiment where we had a few of the cell groups had dried out. I should have picked a different set. Nonetheless, what we're going to look for here is we're going to look at both of these Fmo controls alongside the sample, and we're also just for good measure going to get one of our single stain controls, which we're not going to use immediately, but we'll come back to in a few minutes. So I'm just going to put that to the side for now. Just over there. So what we can make an assessment of here is that you know, if we sort of just roughly take some measurements here, we can sort of say, you know, there are cells that are going to be single positive or double negative. And I'm not drawing these gates to be super accurate. I'm just doing it as like a visual guide. So it doesn't matter that they're just for the purposes of the workshop. Now, I do realize that this is actually a control which we screwed up at the time, which is why it's not quite as bright. But what you can hopefully see, and you'll see in the other examples, is that this is in fact getting brighter and then leaning over to the left, albeit not quite as high. So what this tells us is that, okay, well, in this case, there is no PESI7 at all. And so you actually see nothing, you know, above this line. There is no signal there whatsoever. You can see in this case that in the absence of PESI 5.5, you're still seeing that patternistic lean over to the left. Now with overcompensation, it's usually reasonably obvious because it's just, you know, it's a population that as it gets brighter, it's kind of mathematically curving over to the left into a space where there shouldn't be any cells. So this one is probably, you know, arguably the easier situation to deal with because it's so obviously, you know, abnormal. So what we could do here is we can take these three next to each other, and importantly, they all need to have the same compensation matrix applied if we're going to make any corrections. So I can then go to my matrix, just drop it down here. So I'm going to put PSI7 on the left and PSI 5.5 on the right. Sorry, as the column. So that's what I'm looking at here. So the value here is 5.6. Now, just to kind of show what happens, if I set this to 0, what we're expecting is this is going to move, you know, kind of over to the right. Now that actually looks not too bad, but it's probably not quite right. It probably actually does require a little bit of compensation. If we, in fact, bring up the single stain and we do the same, what we'll hopefully see is that actually, yeah, it does. If you kind of line these two up a little bit, you know, what we're looking for is to get the median of this group in line with the median of this group. And yeah, actually, it does need to come over a little bit. Now, you can only see this if you actually apply compensation to the single stain, which is always a really good idea because this gives you a really good guide about what the machine is trying to do based on the single stains you've given it. And you know, it tries to help us figure out exactly where we're going wrong. So I'm going to, let's say, make this value 1, just for example. Oh, that's actually pretty close. The machine will, oh, I didn't realize you can move those separately. It's terrifying. Okay, so the machine, when it calculates compensation, will do this much more accurately than I am by eyeballing it. It'll actually calculate the median of the positive and the negative and line them up. But for our purposes here, the visual way of doing this just looks and feels a little bit more intuitive. So that's the goal. Fundamentally, this positive, the middle of that needs to line up with the middle of the negative. And if we do that correctly, what we'll see is that this is kind of, you know, sufficiently aligned. This one basically shouldn't have any changes whatsoever because there is no PSI7. And then the sample will look, you know, much better. It'll look like it's kind of aligned correctly. Now, in this case, this is reasonably simple. And then if we, you know, if we sort of went the other direction, say we turned it up too high, they would all be leaning over to the left. So the starting value is, what did I say it was 4, something like that? Yeah, so 4 was clearly too high. Typically, we'd kind of walk it down progressively until we can see that we've kind of corrected what this signal looks like. But importantly, we're doing it with reference to the FMO and to the single stain. It gives us an idea which tells us that we're actually not creating, you know, a population that doesn't exist. We're not doing something inappropriate. This FMO control here is what tells us that that's actually the case. Now, in the next example we'll come to, you'll see that, this seems a bit trivial. You might look at this and sort of say, okay, well, correcting this one, that seemed pretty straightforward. Like, I don't see what the big deal is. In the next example, you'll see why this is really important, because otherwise we might create a population which doesn't exist, which then influences our analysis. So that's really just preventing, I suppose, subtracting some overcompensation that was a little bit too eager. Now, if I was to make it hazard a guess as to why this might have happened, in this case, the single stain and everything seems to be performing fine. What I suspect is that, this single stain control is not quite as bright as the cells that are actually in my sample. And so what I've probably done is not given it signal that's bright enough to accurately compensate it. So, what you'll notice here is if we make very minor changes, because the signal is sort of moving dramatically like this, you could make a small change, like a small change to the number. Signal that's lower down the scale will almost not move at all. Scale that's data that's high up on the scale will move quite dramatically. And so what I suspect is that, within the kind of tolerance that the calculations have, it thinks the single stain has been corrected, sufficiently, but it's just gone a bit too far in the real sample because we haven't given it kind of a bright enough single stain control to really map that full range properly. So if I was to hazard a guess, that would be my assumptions. I probably need to go back and do a single stain control that is more signal, essentially like brighter signal. Either I can use a different type of bead, like there's some capture beads which have kind of just, larger numbers of capture sites so you can get some more signal. Or in this case, I could be pretty safe using some cells because I'll have that full range captured. So that's very important. So that was an overcompensation event that we came across, and we used the Fmo controls and the single stain to give us an idea about how we may go about correcting it. Like I said, correction is like not the first point of call in terms of the data. What we want to do is review our practices and about how we can improve them. But there does come a point where things do happen in the data, and there is like, well, do I just throw this whole experiment out because something has gone wrong, or can I apply a way that is methodical that allows me to make corrections, knowing that it's not going to alter the data? Now, this example seemed pretty straightforward, but there's a different example where it becomes much more complicated. So PSI7 versus PSI5 is the other one here, which we'll come across. I'll just switch this over. PSI5 super stain, PSI5 FMO. Yeah, great. Now, on the N by N plot, this one we actually might miss. Undercompensation is much harder to spot. In this case, that overcompensation, which you can now see has disappeared, it used to be featured here. Oops, it's not showing. That super negative here is gone because we've now corrected that particular issue. Undercompensation is notoriously harder to spot because you don't always have, it won't always stand out in multiple plots. It'll often be much more subtle. In this case, to see this, let's just say we had a different plot, C11b. That doesn't look outrageous. Like you can have cells expressing different levels of NK1.1. This doesn't look like it's, oh, come on, it's not updating quite fast enough. There we go. So if I have, let's say C11b versus NK1.1 here, this doesn't look terribly outrageous. Like you can have cells that express low NK1.1, like this middle group here. That's not terribly, out of line with what we might expect. And so we don't really get a red flag here that something has gone wrong in the same way that we might if we had that super negative. So I really need to kind of have checked the actual combination, of the offending fluorophore and the target and the non-target detector to see this undercompensation problem. So these are much harder to spot because you really have to go and check each of these combinations. But essentially the same rules apply. So we've kind of identified and flagged it, and now we want to go and see if, is this something which is genuine or is it something which is not real, which we need to correct. So we have the same sort of deal. So here is our FMO for PSI7, where there should be no PSI7 signal whatsoever. And here is our FMO for PSI5, and there should be no PSI5 in this sample. And then here's our single stain as well. Now, in this case, because I forgot to set this up correctly earlier, but there is another example of this in case 2, which we'll come to. When I changed this, I didn't change it quite enough. So the example that we're going to apply, yeah, should have gone with a different one. That's fine. We'll come to some of this in case 2. What we're seeing here is that you actually have with the FMO and with the single stain, you're getting a leaning of this population into the NK1.1 PSI5 detector. Now this can be a problem because what you have is the PSI7 signal, in this case Ly6C, is starting to look like it expresses NK1.1. This creates a population which you may miss. If something is super negative, it's kind of obvious. You're like, well, that looks absurd and that can't really be there. Whereas you may well have NK cells expressing high levels of Ly6C. And so what we need to do is kind of, like before, we lean on the FMOs to give us some kind of instruction. If I just modify this a tiny bit to make the effect much clearer, to make it a little bit more excessive. Yeah. So if we look at this, if we look at the FMO in particular, there is no NK1.1 signal, no PSI5 signal in this sample at all. Like we've physically not added the antibody, so therefore that detector should have no signal whatsoever. If we're getting a situation of undercompensation, where we're getting that kind of classic lean to the right, we're going to start seeing PSI5 signal show up in the FMO. And it is because the PSI7 is pushing, across into that detector. So this is kind of where we identify that something is going wrong. And I mean, this is just a really simple one to lean on, that like this sample physically cannot have PSI5 signal. There's just, it wasn't added, therefore it cannot be there. So if it has apparent PSI5 signal, it's coming from spillover. We may actually notice this by looking at something like, let's just say forward scatter in this case. That doesn't look incorrect necessarily, but what we have to realize is that nothing should be in this PSI5 detector because it doesn't have that signal. And so obviously in this case, we go hunting and we see that, yes, it's a spillover event. So what we can do is we can increase that value. Let's say we go for, maybe 10. And now we've gone too far. We've kind of flipped the problem the other direction. So 10 is clearly too excessive. I think the real value was 4 or something. So if we go for 4, no, maybe I was wrong. Maybe it was a bit less, but that's still a little bit too far. We can probably bring that back a little bit more. That looks pretty good. So by being able to take the control here versus both FMOs and the single stain control, we get a pretty good idea of how these adjustments are going to correct either over or under compensation, which can make things reasonably straightforward to deal with. It's not the only situation that we come across though. So we had a look at examples of overcompensation, which leads to that super negative, and examples of undercompensation, which kind of creates double positives, which may or may not make sense. And we also looked at how to use the FMO to kind of help us validate the findings. There is a third situation which we'll come across, and then we're going to have a look at a few like bespoke kind of weird tricks with how this works. But the third classic, which we talked about before, is the spreading error. This one is a situation which we don't necessarily have a solution to. It's more like something that tells us there's something wrong, and then we need to go back and think about how we want to deal with that. So same sort of situation. Take away those gates because we don't need them anymore. If we, in this case, have a look at, let's say, these two. Oh, there's actually one that I didn't realize was in there. Oops, oh, it's in the other workspace. Okay, we'll come back to that in a minute. The classic thing here, which can come up, is when we get pairs of fluorophores that look like they might be the culprit, but they don't really make a lot of sense. What do I mean by this is like when, let's say, like something just isn't right. There's something wrong with the way the data looks, but you don't know why. It's like you can see kind of evidence of that curve, but it's doing it in a way which is not consistent. So let's take this example. So this is one I kind of prepared earlier. I'm just going to expand this a little bit to make it easier to see. So here we have, in this case, this is PCF594 on the y-axis, and this is BV605. Now, on the face of it, this kind of looks like a classic overcompensation. So as the data is getting higher, it's leaning over, but actually it's clearly not, not the full story. And for two reasons. One is that we've got two aspects here. So one is that this is still here, and the other is that this pattern doesn't really, like, there's two kind of separate, you know, spillover issues happening here. This doesn't look like classic overcompensation. And yet it's all positive for this, you know, it's all happening in kind of stuff that is positive in this detector. This is where things get a little bit tricky to kind of work out. So this isn't the offending fluorophore, but whatever is happening is related to this fluorophore. Now, in this case, well, we can probably assume a couple of things. One is that if we know what marker this is, that actually might give us some clues as to what's going on. So in this case, if we just have a little look, that should be CD3. So all of the events that are kind of being moved around are CD3 positive. And this actually gives us a bit of a clue. So it's not CD3 that's the culprit, but it's something expressed on CD3 positive cells, T cells. So, I mean, in this particular panel, we've got, you know, a couple of options, but obviously the main ones are CD4 and CD8. And so it's possible that it's actually CD4 or CD8 that's the culprit, because we know that they are both highly expressed on CD3 expressing T cells. So if we take a look at CD4 first, no, that's not really it. Like we're seeing the super negative, but it's not that kind of mathematical lean that we're kind of trying to find. The other obvious option here is CD8. And yeah, sure enough, that is the one. That's the curve that we're looking for, that kind of tells us that there's overcompensation going on. This example is reasonably straightforward. Like it's a bit of let's say like a diagnostic process to say, well, okay, something is happening here and it looks like it is on cells expressing CD3. And that kind of gives us a clue as to what might be happening. The worst that happens here is, you know, maybe it's like, you know, you see this with let's say, I don't know, if you had a sample that only had CD4 T cells, and, you know, it's leaning over in both CD4 and CD3, you know, which is actually the correct one. You don't necessarily know, is it CD4 that's overcompensated or is it CD3 that's overcompensated? But this is where we come back to using those controls, the Fmo controls and the single stain controls, and that gives us a way of making that assessment with a lot of clarity. So this is really important. So in this case, if it's CD8, that's the issue. If we want to go and correct that, we can open up our matrix. So same rules, BV785, so we find that row, oops, and BV605 as the column, which should be this one. So the value there is 20, in case you can't see it. If we reduce that, actually I'll open up the Fmo while we're at it. Otherwise I'll be doing this blind. BV605. And for good measure, we'll also get the BV785 one. Using the correct order as well. Cool. So if we change this value, so starting at 20, we're going to just walk it down. So let's say we go for, oops, we go to maybe 15. Okay. It's improving, but it's not there yet. Let's go to 10. Also better, maybe 5. Getting pretty close. This one looks like it's going to be just about 0. Oh, maybe it is 0. Easy. Probably just a little bit above 0. But as you can see, what we, you know, by using both the Fmo and the fully stained controls, we actually get a pretty good mapping of how this is supposed to change. Now, if you're doing this without Fmos, the real trick is that you don't 100% know if what you're doing is unreasonable or not. Now, I have a brief example of this just to kind of, I suppose, make the point a little bit. There's a couple of combinations here which give some, I'm going to call kind of classic patterns, which we need to be able to deal with. So in this case, there's this is Ly6C versus CD45. Oops, CD45. Ah, dang it! Come on. Now, one might look at this and think, actually, there is a bit of a lean to that, like as it's going up, it is kind of leaning over to the right a little bit. But if we consider what's actually happening here, CD45 is going to be highly expressed on, all of our immune cells. And this is actually going to lean in this case because these two markers are highly correlated. And if we look at particular things like, let's say, CD4, like this kind of pattern can be quite different. T cells have high CD45 naturally. They already express very high CD45. Whereas if we look at something like Ly6C, which in this case is expressed on various cells throughout the bone marrow, we actually do see that as it gets higher, we get more and more CD45. And so how do we know that this is, like, can we tell the difference between whether this is undercompensation that we need to correct, or if this is just biology where these two markers are correlated? That can be really tricky. Obviously with the FMO, that gives us a pretty big clue. So if we go to the FMO, or in this case, CD45, then we get sort of, we get an answer which actually helps us quite a bit. So, I mean, notwithstanding the Ly6C problems, we actually get a pretty good clue that, if this is a bit higher, we actually do see that this is a genuine population which is highly correlated. If, this showed a population which is, sort of out here on the edge, if I'm just going to draw it in red, if we saw it kind of sitting out here or something like that, as these populations were leaning over, we would actually get a pretty good indication that this is, undercompensation. But if we didn't have an FMO present, if this sample is just not, not here, then how do we know for sure? And the answer is we can't actually know for sure. The FMO gives us that confidence of being able to make those measurements and make those comparisons in a way which is accurate. If we don't have the FMO, then we could have, markers that lean because, well, that's just in the nature of their biology. And I think that the key thing there in terms of the pattern we want to look for, which just gives us at least a clue of where to go for, is that kind of mathematical relationship. It's when we're looking at spillover pairs, something spilling into another detector, we're looking for, as it's getting brighter, it is by definition getting brighter in a different detector, as opposed to, it's kind of higher in one detector and then there's some of it which is expressing higher levels of, another marker. We really want to see that sort of that long string of cells, which kind of, it's like mathematical, right? As it gets higher in one detector, it is by definition increasing in another detector. That's the key thing that tells us it's something which is happening, which is mathematical as to biological. Pretty much any time something is directly correlated between two different channels, something has gone wrong. Now that's not always the case. If you do things like in T cell work, the actual TCR and CD3 correlate really strongly. And so if you have, TCR alpha beta or gamma delta against CD3, it's, more or less a straight line. It looks really weird, but that actually makes sense. Biologically, those two are perfectly correlated. Whereas most of the time, things don't correlate one-to-one like that. You might have, like cells that have, a certain level of expression and then some that have a higher level, but it's not going to be a line. It's going to be two sort of balloons of cells, which kind of, they do correlate, but they don't correlate one-to-one. They don't create a line. And so if you see lines or you see perfect curves, that kind of tells you something that something is likely to be wrong, except for very specific situations where that might happen, such as TCR staining. So those are the classics, which are the easiest ones to look at. There are some situations where we get things like spreading error, and those are things that we really just can't do much about. Now, while I get the other workspace up. So we went through a couple of examples, undercompensation and overcompensation, and some weird things that happen in undercompensation that can kind of throw us off our game. And we looked at how to use the FMOs to kind of help us navigate through that space. Just while I get the other workspace loaded, did anyone have any questions or comments or objections to any of that? Or just things I'd like to add?
Hi, Thomas.
Hey.
Thanks for your explanation. I just put a question in the chat. If we see a negative values, what's the main reason?
Yeah, that's a really excellent question, Teddy. I did say it earlier, but I had intended to kind of come back to it as one of the examples. The negative stuff is tricky. So essentially, I'm going to maybe just sketch this. Maybe that's the easiest way to do this. So if we have, let's say, I just need a white background. Cool. So by default, I think the reason that negative, so I mean, if it's a very low negative value, sometimes that can just be measurement error, and that can be okay. If it's like negative 0.001 or something, that's probably just innate error. Like it shouldn't happen, but there is like a small, I guess, window for error that might be okay. If you think about how compensation works, if we have, let's say, our negative population here, actually that's not the most helpfully drawn, negative population here, and we have our positive here. So let's say this is for two pairs of fluorophores that have no spillover whatsoever. So this is FITC and APC psi 7. So there should be no FITC showing up in the APC psi 7 detector. So the value of this, let's say it's, oops, well, whatever. Let's say that's 10 in the APC psi 7 detector. Let's say that's 10 as well. So by definition, the compensation value is 0. This is perfectly in line with this. If this population, so let's do this in blue, is like over here somehow, and the value is 20, then the ratio. Well, I guess we haven't really specified a ratio, but this value stays the same and this one changes. And so let's say that was 100. If these two line up, then that is literally no different. If this is moving across, then the compensation value goes up, right? And so this compensation value would be higher. If we had, the population sitting over here, the value would be higher still in terms of the ratio of this to this. Now, the issue is that if we get a negative number, by definition, for it to be negative, this population has to actually appear over here for it to be a negative ratio. So to have compensation of 0 or 1 or 2 or 5 or 10 or 50 or 100 all makes sense, and it all involves populations being on the right here. For it to be negative, a population had to appear here, which really just isn't possible. At a minimum, if there is no spillover, it would be the same as the negative. For it to be over here could happen for two reasons. Well, two major reasons. There are a few reasons. One is that the material of these particles is not the same as these. So remember when I kind of talked about this stuff, where we had what do you call it? The batches of the beads where the positives and negatives had different levels of autofluorescence. That's what could cause this. So let's say this was one batch of beads, it had like a lower autofluorescence, and this was a different batch of beads and it had a higher level of autofluorescence. That could absolutely cause this situation. And so before we've even started with compensation, it already thinks that they're different. And so that could be causing a difference there. The other option is, I mean, depending on exactly what's happening, if for instance we had like these were beads and these were cells or something like that, then it could give us some kind of mismatch like that again, because the inherent autofluorescence is going to be different. So I think those would be the main things. If the batch of beads is different, or if you're using kind of a combination of beads and cells, it's possible that fixing beads may increase like the inherent autofluorescence. I don't know if that's actually true, but if for instance, like these for whatever reason were fixed and these weren't for whatever reason, missed a well or something like that, it's plausible that that could do that as well. Now, I mean, the way fixation works shouldn't do that to beads, but I mean, it's entirely plausible that somehow something is changed by that treatment. So something like that could happen. So it's fundamentally going to be a problem of mismatching the autofluorescence between whatever these events are and whatever these events are. That's what causes it. There isn't really anything in the process that should allow for negative compensation. It's like before you've started, there is a difference in their baseline levels. So I mean, in my case, they're all very low values. I'm kind of willing to put that up to just minor measurement error. But if it was higher values, then like I've made a mistake somewhere, which I need to go back and review. Does that make sense?
Yes, sure. Thank you very much.
Hey, Thomas, quick question. So I know, for example, if you're running an example in a BD systems like Diva and things like that, it doesn't actually give you a negative value. But in this case, if it's negative, like you can't actually put a negative value in, if I'm not wrong. You can only put positives in the comment.
You mean in Diva, like the Diva itself?
Yeah, in Diva itself. So could this be a case of like if you see something negative like that, could it be a case when you export the data to say Flojo and you reanalyze using the comps that you have, and then that's where the negative values could come
Yeah,
out.
that's a really good point. I should have probably just prefaced it. So that compensation matrix I made in FlowJo, not on Diva. So that is a very good point. I hadn't thought about that, but I think you're right.
Yeah.
So yes, this one I did in FlowJo, which is why it enabled me to have a negative result.
Cool.
Yeah, just to add to Eric, I've only ever seen negative comps in later versions of FlowJo, and I just wonder if it's just maybe trying to balance some overcomps it's calculated and to shore things up. But I've never seen negative comps on any instrument associated auto comp. It's only in the FlowJo matrix when you create a new comp matrix in FlowJo that you seem to get those negatives. So not sure if anyone else aligns with that.
Yeah, I mean, I suspect in Diva, because the idea is you can't have negative comp, and so it probably just, baselines at 0. It actually transpires it's helpful having it in FlowJo for spectral stuff, which we'll come to in a few minutes. But yeah, interesting. I hadn't really thought about the difference between Diva and FlowJo in that respect.
I do have 2 more questions.
Please.
So first one is, so this is looking at analysis of data and things like that. But say, for example, for people who are operating in a facility doing sorting for users, when someone brings along their whole panel in, and it could be a new panel or something that they add, they used to be sorting, say, 5 colors, 6 colors, and suddenly they decided to bring in a panel that's like 12 colors, which you have not deal with, kind of thing. If it's analysis, you can sit there for the whole day analyzing. Whereas if it's a sorting situation, they book for 3 hours, and then you've got to get this right. Is there any ways of checking or faster way of doing this other than being experienced in it, kind of thing? So that's the first question. Or does it have to be, once you get used to kind of situations, you really need to just lock down a like you say, methodological way to make sure it's clean and clear so that you don't get messed up data. So that's the first question. Second question is, if a researcher, so a lot of times, if you're a researcher might come around, they know that something like this is happened because from the analysis data. But usually when you run analysis data, you are doing fixed cells, for example. But when you're doing sorting, you're using unfixed cells. Is that fixation causes a big difference in this kind of, or is the trend fairly similar? So if they know that something is always going to give a overcom, and they tell you, then you can fix it quite easily, kind of situation. And the third question is, if you run a sample and someone comes around and say, okay, today we're going to be sorting lymphocytes, for example, then targeting lymphocytes. In the lymphocytes population, across all the 2x2 axis that they're doing, you don't see any overcom, undercom in the positive population. So you don't see any issues triggering anything. However, when you're using bi-exponential, so if you see the squished bi-exponential, that means a lot of negative space, then it likely chance something is having that overcom situation. And this, if you only see that, let's say if you're seeing all cells, you open up all cells, and you do see populations that are going negative, that comes from, say, monocytes or something like that, but the sort day itself, the target is only from the lymphocytes, and they have no issues with compensation. Is that of a concern for sorting?
That's a really good question. I love that.
Sorry.
So I'll do question 2 first. So I mean, in particular, well, I suppose this is good. My opinion on it is that, I know what it's like in the real world. It's like, so I would tell people that, go and optimize this to within an inch of its life, figure out the bits, get your controls sorted. But I don't know, people turn up and I turn up and I'm like, look, I had to hack this together. Can you help me? And I do appreciate that situation. I suppose I get to sit on both sides of the flow purist and, real world work. Yeah, I think having a methodological way of kind of hacking through stuff quickly to look for those errors and, if necessary, change them is helpful. I mean, I think the right answer is don't come to me with bad prep, and so we would try and run something on the cytometer first, know that we've kind of got it solid, and if we need to redo a control, then we will, because that way when we turn up, it's I don't really want the sort operator to have to make decisions for me. I want to just have it sorted. So I think that is the right answer. But I do also appreciate that sometimes things happen, and having a way of kind of hacking through that is important, which is kind of, I suppose, what I briefly showed. I don't really use the N by N for that too much. I do initially, but I'll just check at the very least all the important pairs where I know there might be issues. If it's a panel that I've like never done before, then like that's not a panel I'd be sorting on immediately. And you know, I guess in that case, all I could hope is that the sort operator did their best to run it, but it's also like, that's on me if I've kind of never worked with this before, never optimized it before. That's got to be on me. And yeah, I mean, for sure in that situation, you know, I can imagine maybe you fix your comps, but not your sample because it's sorting, but it's the same sort of deal. Like they absolutely have to be treated the same.
Yeah.
I haven't really thought about that. You're right. Like you might fix your comps so they last longer or something like that. It's like, well, that's a good point, but it has to be the same. They definitely have to be treated the same. I really like your third question. I really like. So it's like, what if it's, you know, comp errors that are happening in a different population that you don't care about? So it's, I don't know, you're sorting your whatever CD4 T cells and there's some kind of monocyte compensation problem. This happens a bit that I've seen even in some of the stuff from the NIH guys. It's like, oh, like the non-specific stuff, it's all the myeloid things, don't worry about it. I think the issue is though that those things can spill into, say, T cell channels, and then all of a sudden you've got a monocyte group parading around as a T cell. That absolutely happens. It happens also just for autofluorescence reasons. Eosinophils, I guarantee so many like T cell gates contain eosinophils, and it's like, oh, they express this thing, and you're like, nah. Then, you know, you look at the side scan and you're like, they're eosinophils. So it's not just spillover; it can be autofluorescence too. But yeah, I mean, if something is undercomped and you know your 14 is kind of spilling into your CD3, then you know you can say, oh, well, we're just getting our T cells, but maybe you're not. You know, maybe you're getting your T cells plus some invading monocytes. So it's. I think the globalist view that kind of looks at everything and corrects all the issues first, I think is probably quite important. Like I can see that like, there are situations where you can get around it. I do appreciate that, but I think by and large, there's a lot of exposure to risk there, which is probably unnecessary.
Cool. Thanks.
My pleasure. Claudia. Claudia, you have your Claudia, rather. You have your hand up. Did you want to ask a question?
Yes, okay. I have a personal experience, and I am working with an assay that use magnetic beads that are fluorescent on PCP and APC channel. Also, this assay includes FITC, PE, and PSI7 and conjugated antibodies. But I noticed that I compensated my experiment, and I noticed that there is an overcompensation between PSI7 and PCP 5.5, that is the channel I choose. And I suspect it's due to my magnetic beads are more brilliant than my PCP 5.5 compensation control. Is that possible, and how could we solve that?
Yeah, okay. I think so. Is this so this is like one of the the Miltenyi magnetic separation kits where it's like got both the metal and the fluorophore attached to the antibody. Is that the idea?
And the magnetic beads are fluorescent. Does not have antibody conjugated with PCP or APC. Only fluorescence in PCP and APC. The conjugated antibodies are conjugated with PE, FITC, and PSI7.
Mm-hmm.
And when I compensated the experiment, I compensate the 5 colors. And I noticed that problem. I don't know if I make a good compensation, or maybe I should only compensate PCP or APC with the other fluorochromes.
Yeah, that's interesting. It's that's definitely a trickier situation. I probably can't answer it accurately enough. Like I think I'd sort of need to look at exactly what the specifics are. But when you have stuff which is by definition fluorescent in 2 channels, it can be tricky. The simple answer is you just pick one channel for it to be the primary channel. And I get kind of, if you could think about it, like it will compensate it out. I don't know, let's just say APC was your primary channel. It will compensate it out of the, the PSP Sci 5.5 channel, if that makes sense. Like in the same way, like PE, we could detect PE in the PECF 594 detector. Like we can see it fine. We just don't want to detect it there. So you could treat it like that, and basically it will just remove it from the detector you don't want it in. So that's the simple version of the answer. The more advanced answer is it kind of depends a little bit, like how strong the signal is and kind of how much that's going to cause problems elsewhere. It's a bit of an optimization process. I mean, feel free to shoot me an email afterwards. I can kind of provide some ideas, but that's the basic answer, without sort of really seeing what it looks like. That's a cool problem though. That's really interesting.
But I suspect that is because in my PCP compensation control, the positive population is well. I try to say that in my magnetic bits, the fluorescent, the positive population is more brilliant than my compensation on PCP channel, and I suspect that this is the problem.
Yeah, I mean that makes a lot of sense, and it might mean that they're just not, like, I guess, fluorescent signals that are going to work well together. So that might be more like changing the assay, so to speak, rather than just getting the compensation right. Potentially, I don't know for sure. It's a bit hard to say, totally, but it might be that kind of a situation. Like we've certainly had assays where like there's just two colors which I know we weren't expecting to overlap, and they do really heavily, and so it was like, look, we're just going to get rid of one because it's giving us a headache. And I think that's often the best approach, because that way things are just easier. It's kind of in the same vein of like, why do 25 colors if your assay only needs 15? Because 15 you could just run and not have to, like spend all this time optimizing, kind of thing. So it's in a similar kind of vein, but I appreciate that's a little bit more challenging.
Thank you.
My pleasure. There is one actually two last things, in fact, that I wanted to just quickly show, which is both good sort of stuff for discussion, but also an important kind of jumping point to kind of not what we're going to tackle today, but into kind of further work. Sometimes we get situations where we find evidence of, let's say, overcompensation, but it's actually not what it appears. So in this example, so this is APC on the x-axis and just forward scatter on the y, and there is kind of a super negative here of sorts. I'll just put that back to red. And so, okay, that's suspicious. Something is, let's say, what based on what we learned before, one of the fluorophores is going to be, overcompensating out of APC, based on the patterns that we worked out. And so, we can reasonably kind of go through our list until we find something that makes sense. But when we find it, what we'll see in this case is that, one of these, this is kind of the process, right? You have to kind of do the work to go through things to find where the culprit is. It's not going to be FITSE because it's never FITSE.
Tom?
Yeah.
Can I just share a little trick that I use?
Please, absolutely.
If you have your N by N open, it's sometimes really easy just to scan through that N by N. So in the case we had FITSE and PerCP, we had those super negatives, and you can just go down the column and then along the row on that PerCP channel, and you'll pretty much, when if you're doing sort of 15 to 25 color, you'll see which your culprits are. And especially for people who probably don't know their dye combinations as well as yourself, it's a really sort of simple way of identifying what the other culprit fluorophore that is leading to those, in the previous case of leading to what that super negative might be. So I thought I might just share that.
Absolutely, that is a really good point. Those N by N plots are super helpful. I do find them a bit confusing sometimes. It's not confusing, but like, I think what it is. It's just the cell density. It makes a decision about how many events it's going to plot, and just sticks with it. And so, I mean, often I have these times where I struggle to like see if it's like low frequency events, and you sort of like, oh man, I don't know.
I think if you go to your CD8 example that was overcomped, I don't know if that's easy to quickly pull up, but you could
find it
remember which one that was, but it was a very thick line.
Yeah.
It was
actually,
a very thin line.
Go back to that should have been in 2, I think.
Yeah, well, you can sort of see. So if you look,
there's one of them at least.
Yeah. So in the violet, or the column that's pretty much in the middle there, you go and point on that and you go down. Yeah, that one. If you go down, you'll see that one looks like it's possibly overcomped a bit, that pair. And then if you go down and then turn right, so scroll down and you turn right on the, all the way down to the bottom. So just you'll need need to get to the bottom. So keep going down, yep. And then you turn the corner and go across for that channel. Yep. So
I see what around the corner.
So
around the corner,
yeah. I find just that way, a lot of my users use that to scan for any overcomp issues very quickly and identify the problem. So
absolutely. And that's certainly like the first point of call is to go to the N by N and have a look around. Absolutely. I mean, hopefully, it does get a little hairy as well, but you can also select FMOs to do this with, which will give you, minus in this case the PSI7, and you can sort of see for each FMO if there's things sticking out, and that I quite like because it gives you, like, in some way it doesn't feel very intuitive, but it's like actually if you find the column and PSI5 shouldn't be there, it's like, oh well, all of this leaning stuff definitely tells me there's something wrong, or if it's the opposite problem and it's undercomp, then it kind of tells you that as well. We just fixed it up, so probably this won't be as obvious as it should be, but nonetheless, very helpful, I think. So very good point, thank you. And actually this particular issue, which is in case 3, well, this one will show up, but it won't be quite as obvious. Like we might end up in a situation where there's, we have sort of, super negatives somewhere and we're trying to find where they are. Occasionally the answer we'll come to is that, like, actually, this is not overcompensation necessarily. This is simply spreading error. So these are in line or roughly in line. Oh, it probably is a tiny bit over, but this spread is just inherent to the data. That's a physics thing which we can't necessarily change. So in this case, it is creating a slight amount of kind of super negatives, down this direction, but it's really not anything that we're going to correct mathematically. That's just inherent to the data now. So if I have this situation, where do I go from here? Well, there's a couple of options. One is I can say, is this really, because there's always going to be some level of spreading error anytime you're performing compensation. Is this really affecting my assay in a way that matters? In this case, probably not. I think the separation kind of, of whatever spread is happening here is pretty minimal. It's not really going to kind of ruin my day with my assay. If this got much brighter than this, as it kind of continued to go up, that actually could ruin my day. So there are definitely situations where you might decide, like, we need to fix this. Fixing it is something where we have to go back to our panel design. A couple of options in this case. If we basically, what we're trying to do here is reduce the signal level here. We're trying to reduce it. We're trying to take it down. As you can sort of see with this continuum, if this signal was down here, it just by definition it wouldn't be spreading as much. It would be a lot tighter. So either we could take the same antibody, same combination, but titrate it down, i.e. use less of it, so the staining is less intense. That's one option. The other option is we can simply pick an antigen for this, for this fluorophore that is expressed at a lower level. So therefore the signal level is lower. Or depending on the kind of system we have, we could just drop this fluorophore entirely and put the, it's Ly6G in this case, but just put Ly6G somewhere else. If we have like a big cytometer and say the panel was it 12 colors in this case, maybe 15. If we have, like a 5 laser or more and we've got 64 channels, I'm not stuck with using exactly these options. I can pick whatever fluorophores I want. A big system gives me flexibility. So I can pick fluorophores that are as far apart from each other as possible. You could, on like an Aurora, you could do probably 10 colors that have almost no overlap at all. In some situations, it's not quite enough. Like you do have to kind of push it a little bit. You're going to have some overlap with 10 colors no matter what you do, but you can get them pretty far spaced apart. And that's just really appealing, like a big system isn't just about absolute power and massive panels. It actually, quite a lot of it is just about, well, I've got options here and I can work around problems that might come up. And I find that very appealing. We often do our small panels on our big systems just because we have a lot more flexibility with the big systems. So that's one option. So those are the options we can take with this approach. The goal essentially is to bring this signal down so that the spreading error is less intense. Of course, we could go the complete opposite direction and do something about this receiving detector. Maybe we can move, this is BRDU, oh, B220, sorry. We can move that antibody to a different fluorophore, which isn't affected so much by spreading error, or we could drop that fluorophore entirely, use something different. Panel design isn't really something that we've kind of set up to tackle specifically here. And there are resources and in fact a workshop earlier today which talk about some of that, but I think that's just an important stepping off point, is that the over and undercompensation problems are errors which are kind of mathematically based. Spreading error problems are related to assay design or panel design, which need to be tackled differently. That's very important. There is one final little application I just want to demonstrate here, but first I'll just tackle, there's a question here in the chat, which I just want to tackle first. Huh, that's interesting. Yeah. So, I mean, everything we've been looking at has been kind of in like a by exponential plot. There is obviously the option to, I'm just going to very, very loosely do this, change these into either a linear axis, which we can then, adjust the settings so that everything's visible, or even in some cases in a logarithmic axis. So let me just quickly adjust this. Oh, that's for the Aurora data, sorry. So the value is going to be a bit weird. Let's go back to this one. Yeah, so I mean, some of these we can absolutely do, particularly looking at linear values, kind of as in the question, particularly down near zero, where we're kind of looking at where the actual problems are. Looking at stuff in a linear axis gives us a very different perspective on the data and on possible errors. I mean, one of the weird things about looking at data in a linear scale is you actually get a really like granular appreciation of how sort of biological data works. I can't have the bi-exponential open next to it, but hopefully what you can see here is that if this axis is linear, the majority of the data is kind of low down, and then there's this really long tail as they start to get higher and higher. Right? I'll probably expand this out a little bit. Oh, come on. Okay. So I mean, I think what this actually gives us a bit of a clue about is because as we're getting higher, the higher we get, the worse the kind of overcompensation is. If we're looking at this with a linear axis, this high end, this is all the stuff that previously was like right at the top of the plot with a bi-exponential. Like all of this was previously like here, but on a linear plot, it actually expands it out. And if there are minor differences, which are kind of pushing the signal, overall under or overcompensating the signal, looking at it in linear can absolutely be a more sensitive way to see those subtle shifts. Oh, that's when the linear. Oh, I see. Okay, I apologize. Well, just to make a point, the linear stuff up for the top end of this thing, that absolutely can be helpful. I realize that wasn't the question in retrospect, so I suppose I don't need to go on about it. But the linear plots can actually be very informative. Is something that I should say. It changes the way we see the nature of the data. Any type of scale is really a compromise. Logarithmic scales and bi-exponential scales allow us a compromise of sort of seeing the high and low stuff in a way that kind of is reasonably relevant biologically. But it actually it is a compromise. We actually do lose some information by viewing it that way. Now, because that's not the actual question, I will go and deal with the actual question, which is probably more important. So this is something you can do here with FlowJo in particular is there is a control here, which in this case is called the width basis. When we're trying to troubleshoot things like compensation or spreading error, we make a decision that at data below a certain value, we're kind of looking at autofluorescence or background. So I'm just going to hit apply for this one. This actually relates to the later workshops we're doing on high dimensional analysis, and we'll sort of revisit some of that. But what you actually notice here is that you know, we get this kind of butterflying of the negative population. So if the center is kind of here where 0 is, you're actually seeing all of this on the left and the right. All of this is actually the one negative population, but there's this effect which happens in digital flow cytometry after we do compensation, where you get this kind of duplicating effect around 0. Now, by exponential plots, they by definition are logarithmic, and then they switch to a linear range kind of in the small area around 0, and then switch back to a logarithmic scale. And so what we can actually control here, it's always opens on my other screen, is how much of that negative space we want to compress into a linear area. Now, a very general rule of thumb, at least when we're doing this kind of in real time, is that the higher the compression, the tidier the data looks. So in this case, you know, as we drag this across to the right, we're compressing the space more and more around 0. And so that looks much tidier. Probably not perfect yet, but like that looks much better than it did before. But as kind of the question alludes to, it actually doing this actually means we're going to see less of the like little errors that might be present there. If we actually expand, you know, or sorry, we reduce how much of that space is compressed into a linear scale around 0, we actually get to see more of that potential error, and we get to see, and you can actually kind of see a bit of evidence here. Like this is actually slightly shifted over to the left. There is more cells on the left of that line than there are on the right. So that actually does give us a little bit of a clue that, you know, things have actually been pushed a little bit too far over in this case, which is good to be aware of. What comes alongside that is the ability to control how much negative space we see as well, controlled by this slider. That's simply just how much space there is on the left-hand side, effectively. During troubleshooting, we tend to turn that up to max just so we can see as much information as we can. Once we've nailed it, once we sort of think we've got everything correct, that's when we tend to then like compress things again to sort of tidy it up for, you know, let's say the biological analysis. So at this point, this is more interpretable biologically than sort of technically. But a very good point. That is something which is, I think, like the first step we kind of teach new students that come through the lab, for instance, and it's kind of, you know, very helpful in doing this sort of stuff. So the very last thing I just wanted to show briefly is that in unmixing for spectral data, I'm just going to switch that back. The approach is actually very similar. Now, the unmixing itself, let me just correct these back to where they're supposed to be. The unmixing itself, which is done, for instance, on the Aurora, if you're using the SciTech instrument, that is done in a very different way to compensation. The actual math behind it isn't terribly different, but the overall process is different. We're integrating signal data from multiple detectors and kind of turning them into one, let's say, synthetic detector, like virtual detector. And so what you end up with, you know, is a series of detectors, even though we've got, say, this is on a 3 laser, so not 64 detectors, but rather than seeing each individual detector that the Aurora has, we end up with a consolidated, you know, virtual channel, which represents the single fluorophore. And as a result, we can, you know, view, in this case, PSI7, Ly6E versus PSI5, NK1.1, almost as if it was made on a conventional cytometer. But the way that we got there is potentially much more elegant. It's taking the entire spectral, you know, signal from each of those colors and integrating them together. But what you get to see is something that looks like conventional cytometry data. Now, you can have, at this point, over or under, I'm going to call it extraction, but it actually will look the same. And if you interact with this data in FlowJo, it actually will look exactly the same. But the key difference here is that in FlowJo, you have a matrix which is full of zeros. Essentially, the reason for this, this is the one where we already started playing with it. The reason for this is because this is like not compensation. We're actually not compensating, you know, one signal, one fluorophore out of a different detector. We're actually integrating signals together. And this matrix of zeros is really just to allow this data to show up in FlowJo in a way that's kind of consistent, because otherwise FlowJo thinks you're dealing with uncompensated data, and that creates some problems. So it gives you a matrix of zeros so that FlowJo can see it as if it's compensated, even though there are no values here, apart from the ones where we've been messing with it. Now, it is interesting though, if we apply values here, we actually get the same effect we would see before. So let's say PSI5, we find that, and we look for the corresponding detector, which is, I think it's that one. So if we increase this value, PSI7 spilling into PSI5, if we increase this in a positive way, it actually will push it over, much the same as how normal compensation would work. Maybe that's a bit extreme. Let's just go for something like 2. So we actually do push the data across because it is a compensation matrix of zeros being applied to integrated data. And, you know, in reverse, if we go and do a negative number, so -2, it will push it to the right. It's a little bit counterintuitive to think about it this way, but after the data has been integrated, after the unmixing has been done, we can correct the individual integrated signals if we need to. So you may get a situation with your unmixed data where you see something like this. And as we talked about before, prevention is better than cure. There are a number of things that we can do that can prevent these kinds of issues from happening. But the way the unmixing works is that, you know, let's say it is not being fully extracted. At this point, the unmixing has been done, the signal integration has been done, and we can make small adjustments to the integrated channels at this point, just simply by adjusting the matrix as we would before. It's really a bit weird because we're starting at 0 and kind of going positive to move it to the left or negative to move it to the right. It's very weird to think of it that way, but it actually works the same way as a normal compensation matrix would. And much the same as the normal matrix, we can do that using the sample alongside the FMOs to make those assessments very carefully, so we're not just kind of arbitrarily moving populations around. So if, you know, like you can also deal with, like, if it's kind of just there's been a problem with the unmixing, you've kind of not picked the right population or not the population that's, you know, sufficiently high, that can absolutely be addressed in SpectraFlow in the actual software on the machine, and you can re-unmix it. If it's kind of like, you know, that step has been done properly, but as we've discussed before, your control just simply wasn't bright enough. It is absolutely better to go and solve that in the lab to make sure the assay is solid, but in your data, if that needs to be corrected, this is how we can do it in a sort of a fairly simplistic way. Obviously, if you're using FlowJo, it'd be different in other softwares. But it behaves the same way. Positive numbers move it across, negative or lower numbers, you know, move it to the right. And we should do that in a way that's methodical, relying on the FMOs and the single stain controls to inform our decisions so that we can validate what we're doing. Cool. So those are the main things. Just the final kind of point I wanted to make is that if you did want to learn more about either the analysis with these different technologies or indeed the panel design, I have got a little resources page, which I was going to just provide a link to. This is simply so that if you're kind of, I guess there's a lot of things brought up here, which we can talk about. But sometimes it's like, well, okay, like you kind of mentioned that going back and doing the panel design is what needs to happen. But if, you know, if there's no kind of, I guess, you know, place to go, then it kind of just leaves you in the lurch. So in the chat, I'm just going to drop a quick little URL. I put just a couple of quick links to some panel design papers that I really like. A couple of them are from us, one on sort of high dimensional panels and the other is comparing spectral cytometry to conventional cytometry. The two others are from the guys at the Malgan who actually did a workshop earlier today on panel design. I've just linked those papers in there as well because I really like their kind of new take on doing panel design for spectral work. So that's really important. So those are just links just to kind of give some clues, and I'll put a link to the slides from before on there when we're done as well. And there's a couple of just other links there, some webinars on some of this stuff as well. So those resources might help if you're kind of then, well, I need to go do some panel work, which is fine. But otherwise, that's all the main material I had. If anyone else has any questions, feel free to stick around and chat. But otherwise, that's it for the primary content. So thank you very, very much for attending and participating. We really appreciate it.
Hey, Tom.
How's it going?
Good. Hey, just thought of a reason people might get negative comps in FlowJo. If they stain, say, lymphocytes with CD3 and they don't use a a lymphocyte only negative population, then you're going to have higher autofluorescence in your monocytes and whole blood granulocytes, and then it's going to FlowJo's going to try and make that a negative comp to bring it back with a median of those higher autofluorescent negatives. But yeah, I think that's only, I don't know if Eric would comment. I don't think that's going to happen in Diva. It'll just keep it as 0 probably in that channel.
Yeah, I think in Diva you just keep it at 0. But
yeah.
So this was something that I've seen back in the days PhD when you try and stain everything in there, like 5 stains for lymphocytes, 5 stains for say macrophages and eosinophils, and then you try and comb them together. It just goes nuts. So I've got to sort of duplicate the data, 2 sets, 1 set comp only gate for the lymphocytes and then comb using that way, and then the other set gates on the macrophages of eosinophils and then comb using that way. But based on what Tom was saying, my understanding or question would be, because in FlowJo, for example, if you're doing a sort using Diva, there's 9 levels of gating strategies that you can only get so much before you lose that view of your population that you want to look for. So would it be because of that, therefore you go with doing proper comps across everything, gating for the fluorescence that you're looking. Say for example, if you're looking at lymphocytes, you would just gate for CD3 positive from there and move on, rather than you gate for your lymphocyte population and then gate for CD3, which sort of doesn't really, I mean, they are redundant gates per se. So you save 1 level of gate, but by doing that, you really need to get your comps correct before you actually gate, because if not, you will see what Tom was saying, the over or under comp.
Things can
you
sneak into another gate, and you don't.
Yeah, that's right. Yeah.
That often, you know, that's a sort of an issue I see often with analysis with users, is you have a gating strategy for analysis, and you may not see one of those super negative sort of things happening, or that in your gating sort of structure of just going through your bivariant plots. But because you don't see a problem doesn't mean you haven't got a problem there, and that can so that's that's another really useful thing about the N by N. It can really reveal things that people look at data through their gates in a bivariant plots, and it's like, oh, it's fine. It's like, oh well, no, you've got a big comp issue here, and it's putting these cells into that gate, and you don't realize by just looking at the bivariant plots you've got listed there. So
yeah, definitely. I mean the different autofluorescence for different cell types thing. Like I do a lot of myeloid work, so this is like my my big
they've broken rule 2, haven't they? They've compensated something to a different matrix or different substrates autofluorescence. So it all comes back to abiding by those rules of comp to get it good. So, but yeah, so I
had thought about whether to kind of bring that up, but it's like
like maybe 2 hours.
Right, it's like maybe that's a different workshop, because that we do a lot of in the spectral work now is that kind of autofluorescence based stuff, and so it's more prominent for us now as in terms of our practice. But yeah, I figured it was probably too much for a 2-hour session.
I just wanted to comment on that, and I think it's in line with the same things and of the negative comps. I'm working a lot with skin, so obviously skin is super highly autofluorescent, and I'm also interested in myeloid cells in the skin, so it kind of doubles up, and we then get these negative compensations. When we work with Calusa software, you can actually put in negative values as well. So Calusa allows for that as well. But also, when we have in the last couple of years embarked on the more larger panels, around 20 colors, and actually make all my students first do the N by N before they're even allowed to look at any analysis.
Yeah, that's
make them sit there, and I let them at least do 1 round of N by N. But I also find that sometimes when we have minor things that need a little bit of adjustment, you almost need to go a 2nd round through to make sure everything is then really up to scratch. And, you know, and they usually spend the first 2 to 3 hours only doing this, and they're often not happy with me. But like David says, like, just, you know, in your gating strategy, you wouldn't see it unless you do this very methodologically. And so I think that's really, really important to actually do that in that quality control.
I really like that approach. I also like it because I would imagine it has this unintended effect. Like, this is something I do with people I train, but like, they get so irritated having to check it so thoroughly and like make corrections, and it makes you go like, oh man, it'll be easier just to like do the controls again. And it's like, well, you know, like I suppose it kind of reinforces this, like, it's so annoying to have to do that it kind of makes you really focus on getting the controls right. And so as a result, then when you check stuff, it doesn't take very long, and you're like, oh, it's great, no issues. And
yeah,
it just
absolutely.
Somehow it enforces that, which I quite like.
Yeah, also, you know, that they really understand what the after effects are of a specific, even if they would never analyze the bivariate of a certain combination, but it ripples on, right? And I think that's really important to understand for them. But also, you know, working with more challenging tissues like skin or brain, I also feel like whenever we do a beat compensation, it will never be 100% accurate. Like, I haven't been able to get it 100% accurate. There will always be some issues just because the tissue in itself is so challenging, and there's this heightened autofluorescence in there. So I'm not sure what the solution to that is, apart from, you know, doing a manual correction afterwards.
Yeah, I mean, certainly with the Aurora, we've had a much better go of kind of dealing with highly autofluorescent stuff, just because I suppose, you know, the conventional way makes a lot of sense in like blood, where everything's quite tightly controlled. But yeah, I mean, we do this stuff with brain, and we can kind of get it to work well with sort of very few corrections. But I definitely appreciate that, like, messy systems are messy, and like it doesn't always play nicely. And yeah, I mean, I don't know, like, sometimes it's like you just got to correct stuff because, you know, there's kind of, like, I'm always torn between, like, I could go and make this better, but like, I also need, like, I don't know, I'm thinking about like the patient this came from or something, and like wanting to have some answers, and I'm torn between, like, do we go and get this kind of perfect, or do we find a way to get on with it, kind of thing. And I don't know, the purist in me yells at me about it, but then my realist is like, I don't know, man, like, we're dealing with, you know, a disease, like, we need to kind of get something, you know, on paper. So I definitely appreciate that difficulty.
All right. Well, thanks a lot for your great workshop. I really enjoyed that.
Thanks for coming.
No worries. Bye.
Hi, can I ask a really simple question?
Please, by all means.
Sure. So when I do clinical assays, when I do a comp experiment, I use BD comp beads, but the BD comp beads, the 45 signal, I always have to use cells. It's always brighter than BD comp beads. Have you found a comp bead that has a signal that's brighter than 45 on cells?
There is, versus 45 on cells is interesting. I haven't made that exact comparison. There's a brand, what is it? I think it's, I don't know what they're called. They're like, I think it's the Ultra Comp bead, but it's like Ultra Comp Plus.
Ultra bright? Is it ultra?
Not
ultra
no,
bright?
it's well,
no.
the one that I have used before is, I think it's because Ultra Comp is a type of comp bead, and it's like anti everything. But there's an Ultra Comp Plus, which it just has more capture sites, and so the signal is brighter.
Okay.
In answer to your specific question, I don't know if it competes with 45 on human cells, but like, that would be the direction I would go. I've had a bunch of people use those, and they've kind of, their reports have been pretty much positive the whole way through. So I would assume that it's at least at a level that's manageable.
Oh, that's great. No, that's generally the only one, unless I'm using Cyto 16 and I need to do cells. But I really love to just use beads for a nice bright signal for everything. Okay, no, I usually check brand new antibody, always check cells or beads. So thanks very much. That's helpful.
I think they're called Ultracomp Plus. If anyone else knows what they're actually called, please feel free to correct me. I think it's Ultracomp Plus from Thermo Fisher.
Thermo Fisher. Okay. Thank you. Thanks. I really enjoyed your talk. It's great. Thanks a lot.
Thank you. Thanks for coming.
Can I just ask a question and get people's view on this? 2 peaks in comp beads when you get that. The people think that's just essentially So what I've tried a few things where if people put the antibody in and squirt the 50 microliters or 60 microliters of comp beads in, it's not as bad as putting an antibody into 2 microliters of antibody or something like that into 60 microliters of essentially bead solution. And by the time they do 10 of them, they come back and they flick them. You then reestablish a different binding equilibrium, because when you put that 2 microliters in, it's probably a local effect where it's a very high concentration. Have you guys ever had that problem, and do you know what causes that sort of 2 peaks in the positives?
You mean like this kind of thing?
Yeah, is that beads?
Yeah, beads.
Yeah,
that looks like beads.
Is that just on singlets, or is that?
Well, so I mean, this one is not. This one's on the doublets. Even sometimes when you gate singlets, you see these 2 positives. Ah, interesting. Okay.
I don't know. Have you guys ever encountered that? As I said, I did a few experiments, and it did sort of. It's mainly users will come along. They got these 2 peaks, and which one do I use? And I did some where if you put, as I said, if you put 2 microliters into 60 microliters of comp beads, you get sort of a, by the time they've got to their 15th antibody and go back and then mix them all.
Yeah, okay.
2 microliters has probably been in a higher staining equilibrium than when they mix it, and then all the other beads get less antibody and less concentration to effectively bind. But I just thought I'd throw that out there because it was just one of those mysteries of life.
I mean, I would totally buy that. Like, I think most of the time it's doublets, and there are some occasions where it transpires that someone had added a second antibody, and so it's not like a double peak. It's actually P Psi5, so it's a bit less bright in the Psi7 channel. But like, I often wonder about this kind of thing, because antibody binding is actually really fast, particularly with the capture sites. So I could totally believe that such a thing was happening as you've described it. I don't think I've seen that really, but like, I'd certainly be willing to believe that that's something that could be happening. Just not my personal experience, but I could totally appreciate that might happen. Definitely.
Steve has a hand up for quite a while. You want?
Thomas, thanks for your presentation. It's great energy, just terrific on a very technical subject. I'm interested to know how much influence voltage settings have for you. The questions about negative compensations may be relevant if, in fact, the voltage setting of your negatives, or negative populations in your comp, or your negative populations in your assay, if you've positioned those too bright or too dim using voltage, by the time you come to compensation, the numbers might be skewed. Have you had this experience?
I mean, certainly not. So for the negative values thing, the negative comp values,
the negative population.
Yeah, I mean, so I mean, if the comp value is negative, that's really got to be more like a mismatch type of issue rather than a voltage thing.
All right.
I mean, so the voltage thing, it is really important, but not in the like balancing the voltages type of sense. Like each independent. I mean, the biggest thing is that we'll come across is like the signal is off scale, and so once it's beyond the linear kind of upper linear limit, we can't compensate it accurately, and so it will just be a smush, and that comes up a fair bit. Ly6C actually is the one that like every time I give someone a panel, I know what's going to happen, and it always, well, if I don't think to mention it at the time, it usually does. That absolutely plays a big role in messing with comp, but if it's reduced to the extent that it's on scale inside the linear limit, at that point everything is pretty good. So I mean, I guess the detector stuff individually, they do have to make sure the signal's on scale, but certainly like trying to balance voltages between detectors to like reduce comp values and things like that is definitely not necessary.
No,
that doesn't really make any contribution.
No, it's a mess.
And I mean, like, it's, even though I get it, sometimes I'm saying like, there might be something where it's, the comp is 80, and there's a little part of me which is like to change the voltage, and make it lower.
No.
But it's, I mean, which is silly. And I mean, I had a thing that I was considering showing it today, but I decided not to. But showing exactly what happens and showing that you don't need to do that. But yeah, certainly getting the upper signal correctly on scale makes a big difference, because we for sure get situations where it goes above that, and then correcting that is a complete nightmare. Well, we can't correct it. We basically just have to cut that data out and sort of hope we haven't lost anything or lost anything important.
Just to that point you mentioned there, Tom, about voltage balancing. Do you have any views? Because I've spent a lot of time like monitoring our electronic noise on our systems and giving users what essentially we try and hit 3.5 RSD for our negatives, and then obviously if something's off scale, then the recommendation is to titrate your reagent rather than drop your voltage. But obviously in a lot of the 26 color panels that we've been sort of setting up, you're going to have 5 or 6, I would say, comps over 100%, and as long as they're in dyes which are not mutually exclusively expressed and stuff like that, it doesn't really complicate it. And I suppose some users are very into voltage balancing just to have comps under 100%. Do you sort of my view is I'm very against that. I just think it's your spread doesn't change with voltage changing. So do you have any views on, have I got the right tact there, or am I going down the right track that probably avoiding voltage balancing getting a comp under 100% is less important than having a well-resolved population and dealing with spread after that? That's, I suppose, my question.
Yeah, no, that's spot on. I mean, I put this in the chat just for good measure, but whilst I was struggling with it, actually, well, no, the story comes in 2 parts. The first was when I was a grad student, when I was starting out, and someone would explain. So I sat down with Adrian and we talked through the voltage balancing thing, because that's what I got taught. And then he kind of was explaining like, hey, you don't need to do that. And we talked it through, but I couldn't quite believe it. Like I sympathize with users who are like, who stick with it, because I was there, I remember that. And it wasn't until I think I ran the stuff and I saw in the data and I was like, oh yeah, it really doesn't, like that really doesn't affect things. So that little thing I dropped in the chat is like just a tutorial we did, which it was the data set that back in the day helped me understand it so that I could sort of let go of the desire to do that. And because I found it really hard. It was like, I couldn't quite picture how doing that would, it absolutely makes sense in retrospect, but at the time it was like, I couldn't quite get the concept. So I mean, you're completely right in that approach, and sort of that is not the thing that matters. Like optimizing the individual detectors, having stuff on scale, that's very important. Balancing them.
I think it's that concept that people don't like. The minute you see that spread doesn't change with compensation values, or changing your voltages to change your compensation value doesn't affect what your spread is. And when people can understand that, then they realize there's nothing they're gaining from it. All they're doing is possibly diminishing the resolution of their marker because they're dropping their voltage lower than, and dim stuff's going into electronic noise with their negatives and stuff like that. So yeah.
But definitely the right tack. I think it's really important for people. But like, I sympathize why people find it hard to let go of, because I was that person. So I do appreciate that, like being patient with people and kind of like, easing them into it is probably, like, I think it pays dividends, because I mean, I guess people will find it hard to let go of stuff like that. I mean, I did. So yeah.
Can I quickly comment, just make a comment back to the earlier one where you guys are talking about com beats and then having double peaks, or like quite a wide spread out on the positive peak kind of thing. We've seen something like that quite commonly. When researcher brings their com beats in for compensation, it's an interesting thing. So what we find is that when they bring it in, it's either the positive population will be really small. Usually you expect about half-half kind of situation, because they would mix, they would stain first and add in some positive beats from the same batch kind of thing. Or what will happen is the positive will be like really spread out instead of a tight peak kind of thing. And we find that if we use our fingers to tap and try and mix the tube, it still stays the same. But what we need to do is either do a hard vortex or we rack it against a tube rack or on the rails of the hood for solder kind of situation, then it somehow breaks it apart, and then when we run it, we have that 2 tight peaks. But we leave it on the table for like a minute or so, like as you're going through the comps and coming back to record them, it somehow goes in that mode again, and you got to rack it again, and then it sort of breaks it apart. Sort of like then it becomes 2 tight peaks again as you run it. So I don't know why that happened.
Eric, do you see anything change in your physical parameters when you do that? Or do you see
physical,
that, like foresight?
The scatters, yeah.
Does it look like the speeds go less activated or anything?
We
Nothing.
never really take note, although when you're running the comps, you will see your first plot is always the forward scatter, side scatter plot.
Yeah.
We don't notice that positioning of the population changing. Like, you think that if it's doublets, you might see it being bigger or something like that. We don't see that because, or at least our gates are maybe too big so that it didn't move out again. We really notice it moving that much more, but the signal part is definitely different. It's either sometimes we got 2 peaks or a very broad peak positive, or it will just this peak will just disappear and the negative peak will be sort of like wide, and then when you rack it, both peaks will become separated and sharp again, kind of situation. And I don't know whether that's similar to what you're seeing. And the other thing is, you were saying that if you had put 2 microliters of antibodies into 60 microliters of beads, and then do that, and by the time you come back, you got some beads that are stained more, some beads that are stained less. But I assume that when you're doing this kind of staining, whether you do titration or not, you still want to get it to a saturation stage. So if you have mixed it, it should saturate all your beads, and all your beads should be similarly stained, right?
I think what happens is people will, and it may depend on the antibody, I'm not sure, but people will go and, you put 2 microliters into that 60 and you do 12 of them. By the time, and they'll do all of that, they won't mix them individually, and by the time they've got through all that, they've probably spent a minute, and then they go back to their first tube, and then they go through and flick their tubes. So I've done a couple experiments. It seems to validate it, but there may be biases in it, that if you flick it straight away or you add it the other way, you get less of those 2 peaks happening. But yeah, I'll try the racking it, or a good hard vortex next time I have a user asking about it and we see it. So but yeah,
cool.
Really interesting, because I swear I've done times where I've been like getting some doublets, and so I give it like a solid vortex and it's still there. I'm kind of like, gee, come on. So yeah, I don't know. But beads are weird, and I can totally appreciate there's a lot of like static type stuff, which probably means that they just tend to stick together. But yeah. But yeah,
we don't see that often, but we do see frequently enough to know that it is an issue. And it's from the same group. Different people bring it at different times, can have this issue or not. So it's not always the same person or always the same group kind of thing. So, but more immunology side of stainings. Like if someone comes from cancer group doing staining, don't see that kind of issue happening. So I'm not sure whether is it a buffer that they're using that's causing the issue, or is it the old antibody that they're using?
Do you know what beads they're using?
We never really follow, because most of the time we sort of like we just stop operating. So,
you're like, I don't really care what you're using, just give it to me.
I just wonder if it's a type of bead that they use, like a particular company's bead. Most of the stuff I've seen that I'm talking about are on the BD wrap and the hamster beads. So yeah.
Cool. But today's talk from Tom is really, you've really got to reassess and take, like you say, talk to the researchers and see what kind of beads that they're using, especially with the, if you have a negative com and because of potential batch effects of autofluorescence and things like that. I think that's something that we never really thought about. So thanks.
And the other weird one, which is like a totally pain in the ass one to track down. I didn't bring it up because I figured there's probably not enough time to go into it, but like things like the brilliant staining buffer, like the actual fluorophore interactions that can happen in a mixture, which means that they're now different to the single stains. I mean, it's probably the sort of thing I should bring up, but at the very least, the vendors tell you that, and they're like, here is our buffer that, But yeah, stuff like that, where you're like, oh, for goodness sake, like, come on. It's like up against it at every bloody stage. But at least those things are now quite well known. They weren't well known in the early days of the Brilliant Violet stuff. And these little weird things were happening. We're all like, I don't really know what is going on here. And, you know, yeah, very bizarre. I feel like, well, yeah, I probably should have at least mentioned that in retrospect, but whatever.
Just to follow on the brilliant stain buffer, early doors, there was no recommendation that it be included in single color controls, but now I think BD on their TDS say it should be included in single color controls.
Really? Okay. Interesting.
Yeah. You're nodding there, Eric. Do you agree, or have you heard that as well?
Yeah, I'm pretty sure I've seen or noticed that that clause. Someone has brought it up before in our lab. I can't remember whether it's also I was talking to Andrew from BD when we were discussing Brilliant Violet stain, the kind of, and he did mention that they have. I think it was from him. He did mention that they now put in that clause in to say that, suggest that if you're doing it for your combis, you should be using that as well. So
yeah.
I suppose that also stands. It's like if you're staining them in common buffers and things, that's just better practice for sure. Oh, glutaraldehyde. Oh, that's such a good point, Steve. I mean, that's fine. Nick would go on about this all the time, but like they would like use glutaraldehyde to like induce autofluorescence for like, I mean, controls for a different type of thing. But yeah, so I mean, it's interesting. I don't know of anyone, or at least no one that I work with that uses glutaraldehyde in flow. We did experiment using it in mass cytometry because it was like
it's the typical way we assay for hemoglobins inside red cells.
Yeah.
So it's a popular assay in the diagnostic world for preterm hemorrhage, and so we use glutaraldehyde to partially fix the red cells so that they survive permeabilization. And in the process, we light up all the leukocytes in the sample.
Yeah, interesting. And is that because, like, say, formaldehyde wouldn't do that? Like, or is it just because it's always been glutaraldehyde?
Well, I suspect it's been the fixation, the choice of fixative, perhaps right from the beginning. It's been accepted and adopted sort of almost universally at the moment. So I'm just trying to think, how would we do a compensation panel and include glutaraldehyde if we were going to be especially attendant to that. Luckily, though, this assay is only works with 2 or 3 colors, and we can work with it manually.
Yeah, sure, of course. And I mean, like, I suppose it depends on like how significant the autofluorescence is, but
well, this one is it's the leukocytes right in the frame to be mistaken for fluorescent red cells. So
interesting.
So what we usually do is we compensate in like if the assay's in 3 colors, we might compensate in 5 colors. Then we can exclude the autofluorescent white cells using a color that's not involved in the red cell assay, leaving the red cells behind to be examined. Yeah,
that's pretty cool. Can you still see them, like, see the difference in scatter, or like, because I mean, fixation
in fact, if you get enough cells in the sample, you can quite clearly see the typical pattern in forward and side scatter, so it's anyway, it's a quirky test with a quirky little challenge of autofluorescence.
Yeah, that's really interesting. That's very cool. Because we looked at it for site-off work sort of back in the day, explicitly because the autofluorescence is irrelevant, and it was like, well, it's a hell of a fixative, so maybe that's what we should be doing.
Well, if you don't compensate, they'll interfere with your diagnostic dot plots for sure.
Cool. Yeah, that's really interesting. Right.
I'm just having a quick look at glutaraldehyde, and there's a paper in Frontiers Science in 2019. It seems to talk about all these pitfalls, especially, and one of them was the cause of strong fluorescence in cells. So it sounds like that paper is looking at how to sort of subtly use these and how to deal with this or circumvent the pitfalls. So might be interesting. I'll see if I can. It's on the other I'll see if I can find it and drop the link here.
Very cool. For a bunch of the stuff I do, I depend on autofluorescence to like pull out things like eosinophils. I have this like with a lot of like diagnostic but clinical groups I work with using flow, where they're often not looking for eosinophils, so they don't have any markers for them. But because they're really distinct with autofluorescence, you can kind of quite easily pick them out, like either manually or with a clustering. And so it's like I just depend on it so often now, because I assume like a lot of data I get won't have eosinophil markers, and I really bloody love the eosinophils, and so
yeah,
I can always depend on their weird autofluorescence to pick them out.
If I was to make a comment on eosinophils, Thomas, excuse me, what I see in a lot of samples is that eosinophil granules from disrupted eosinophils are quite sticky, and they start sticking to things, and they can reposition a perfectly non-fluorescent, or make a cell that's non-fluorescent in a particular channel, make it perfectly fluorescent. It can even take it out of the position of your primary gates, so that it turns it into a SKP.
Interesting.
So
yeah.
I work in the diagnostic area, so I can't speak for all the wonderful technology that you do, but also aggregates of any kind will spoil investigations. Aggregates that are caused by typically mismatches of antibody and lyse reagent. I don't know if you've come across this. Yeah, this is the SKP phenomenon, but we might be getting off track here. Not necessarily an issue for compensation.
Well, I don't know. I mean, a lot of that sounds very relevant. I mean, something which I kept seeing in, I mean, I've seen papers that have reported this for COVID, but I don't know how solid an observation this is. But like, you know, like a normal blood plot, you've got a fairly typical projection of kind of the lymphocyte to monocyte to granulocytes as they go up on the forward and side scatter. But in a whole stack of COVID samples, there's these like really high forward scatter but low side scatter, you know, extras, which like they don't really turn up in the healthies at high frequency. I mean, they do sometimes, granules. Yeah, interesting. Okay, curious, because there is a couple of papers describing the phenomena in COVID, and it's, you know, obviously there's a lot of, you know, dysregulation happening during that process, including eosinophil degranulation. So that actually makes a lot of sense. Because like I've been trying to figure out like how I should be like treating these extra cells, and I'm like, oh god, I don't know. Like I've got them in my data, but I'm trying to like have an explanation that makes sense. Like I can show like some of the neutrophils are getting screwed up, some of them are notosing in blood, which is crazy. But these escapee things, I've just been looking at it like I don't know if I want to talk about them, because I don't really know, you know, I don't really have like that's what I think it is.
It is an extremely odd phenomenon for sure. It can be very, very specific. It could be that your monocytes are interested in adhering to your T8 cells.
Okay.
And it's all to do with your choice of lyse reagent and the clones of antibodies you're using. So this is
interesting.
This is something that manufacturers have to work with when they're preparing IVD product.
Yeah, sure.
Their panels and their antibodies, when they say it works in an IVD fashion, it works with a specific lyse reagent under specific conditions. People who want to work with these products and use their own lyse reagents they've got to watch out for the escapee phenomenon, because it sneaks up on you, especially if you get wedded to your primary gates, forward and side scatter, 45 and side. You know, you might be missing all your T8 cells up in the top right-hand corner.
Yeah, interesting. I mean, the thing that I found kind of, well, both curious and really irritating about it is like, it was different populations that were affected. Like in some, it seemed to be kind of more monocyte focused, which I mean, like I can understand, like monocytes and platelets have these kinds of things, but then sometimes it's the lymphocytes and it's like, I don't freaking know anymore. Yeah, very interesting.
It's really odd, and it can happen with any combination.
Cool. That's actually very educational. That's really, I mean, fortunately for that particular,
it's off topic, but there you go.
No, I think it's really cool. Like I you know, fortunately for our analysis at the time, it was kind of, I guess, outside the primary scope, and so it was like we were fine to kind of leave it for some other day. But it's just been in the back of my mind, like I don't really know how to talk through this in a way which makes sense. But that actually is really informative.
You can create pages on your analysis program to hunt for these things before you dive into your diagnostic work, or your, you know, answering the big question. You could prepare a page to hunt for escapees. Then you prepare a page, or you prepare a page for compensation. Then you prepare a page for escapees. Then you prepare a page for flight. And then once you've ticked off those pages to say that none of these things are a problem, you can look at your diagnostic page.
I got it.
And go forward. A lot of workers make just a diagnostic page and dive in, but they might in fact be quickly overlooking compensation, as you do, as your talk suggests. But you can also prepare pages for escapees and flight, and
very cool. I'm totally going to go like dive into this a bit more now, because now you've piqued my interest. So, thank you for that. I appreciate it.
Especially when you're working in the if you're not working in the IVD world, you're vulnerable.
Yeah, I guess that's true. I guess it's a bit more Wild West.
So I was going to shamelessly plug something. We've just got a paper up in Cell Reports. I think they've got the galley proofs back. I don't know if I'll be able to share them on the networking site, but pretty much. I hope this doesn't scare you too much, Tom, but every macrophage you see in bone marrow is not a macrophage. It's cells with remnants of other macrophages that are ripped off in the process. So we've had we did a whole lot of tissues, a lot of imaging cytometry, and then just showing how this confounds actually a lot of the single cell data atlases, like the Muris tabulus data set. When you look at high and low density reads, and you see this complete underrepresentation of macrophages, which I think you also see in I think it was in your Nature, in your returning to the perplexed.
Oh yeah.
One of those data sets. There's just no macrophages in it.
Oh, it's a bone marrow one, of course.
Yeah, and it's like the lead author, but it's just scary. Like, it makes you think, how much have we misinterpreted over the last 30 years using F480 as a macrophage marker? So
I mean, every time I pull it out, particularly with, I mean, actually we start, in the spleen we used to get a bunch of this with the stuff I used to work on, and it was like half of this doesn't seem like it's the cell we think it is, but like bone marrow, every time I look at it, I'm like, nah, man, something's not. It just doesn't look the way it should. It doesn't look consistent.
Spleen.
So that's super interesting.
Spleen's pretty similar in terms. Spleen and liver, you're sort of half and half, or liver's half and half. Spleen's probably a bit higher. Serous cavities, it's fine, like peritoneal pleural cavity washes. Macrophages. So
I suppose they're not really filtering like through stuff so much. Like, they're not like, because I mean, the spleen, you got whole lots of input and then like digesting up stuff, right? I guess in the cavities, it's really just sentinel
yeah,
sort of stuff.
yeah. So you don't get it's the processing of the tissue. It'd be interesting to see what brain looks like as well, because when we first started seeing this, was using F4A, and it was like, oh, is this a localization thing, which we didn't expect. But then we used the Mac green mice, and we saw these little, you know, green dots on the surface, and they're fairly large. They're not small, but you know, that pretty much shows that you know, it's cytoplasm. You know, that can't be localization, because that's a reporter that's cytosolic. So and we also pick up RNA, essentially being, it sort of first came out of some sorts that we were doing, where we were sorting macrophages, and they just had this granulocyte phenotype when we cytospun them. And it's like, is this happening from the sort, you know, sort of just changing them very quickly? But it's actually the fact that they've got little bits of macrophage remnants on it. And it's also seems specific, like for the granulocytes in the marrow niche. If you knock out if you look at CD169, either you know, heterozygotes or knockouts, using a knock-in knockout, you see essentially a depletion of that tethering. So, but I'll flip that paper onto you. I'll see if I can share the proofs, but yeah. So anyway, that's like Steve's escapees. It's another little purposely mixed metaphor, a spanner in the ointment. So
I really love that. The spanner is great. Like, it's so boring when it's just as expected. It's
spanner in the work, when it's a spanner in the ointments, it's even worse. So
well, yeah, spanner in the ointment. A bit unusual, but yeah. That's really interesting. Thank you for sharing that. It's really cool.
Wow. Can I ask one more question? This is something from Hira, who was with us. So, and she has this. She's in from my lab, right? And she's got this question that she reminded me to try and ask as well. She wanted to ask earlier, but I think where she is a bit noisy, so she's asked me to ask for on her behalf. So in our lab, sometimes, you know, you do your comp, right? You run your CSNT in the morning, and it sort of sets up the voltages in general in Diva. And when the researcher comes around, they bring their comps around. We will comp it. But there are a few times where we find that for some reason, the voltage of a non-used channel causes the positive peak to be higher than the actual fluorescence channel. So if you look at, let's say you run V650 or 660, and you look at you look at the same channel, looking at the same for same sample, so same comp beat. Channel V670, you find that for 650 it's at 10/4, but 670 somehow is at 10/5 or some between 10. It's higher than 650 itself in the 670 channel. So when you try and comp in this situation, it would cause an error. It will say it won't allow you to comp because it's way at high end. The values of a comp, I think, is way past 1,000 or something like that. So one of the things that we're trying to do these days is any channels that we don't use, we reduce the voltages down to, say, to 400 to start off with, kind of thing, and then we run the actual comp based on where we want to set it, kind of thing, and that has solved our issue that we see in this situation. But it's always in our mind, and the question is whether is that the correct way of doing it, or is that an ideal way of doing it in the kind of situation. I
totally sympathize with that situation. So we used to get this a bunch with, like, we do like adoptive transfers and things. Like, the membrane dyes are really bright, and so we take the voltage down in the nominal primary channel, and it ends up being like 1,000% comp in the non-target channels, because we haven't taken them down too. It's kind of like, it's just like, come on, man, I'm not even using it. Just like, and it's one of those things where I'd rather just let me get on with it. But so, like, is it the right thing to do? I mean, I don't know what's right. Like, so, okay, a detector you're not using, the voltage for that can be whatever. Like, you could just as easily like delete that detector, kind of thing.
Yep.
So yeah, I mean, I always appreciate keeping extra data for troubleshooting. So yeah, taking the voltage down in the other ones, I mean, if they're not being used for anything, then yeah, I would appreciate that is probably fine.
Mm-hmm.
I mean, I suppose the other option is stuff like, I get this with the the PSci5 is always going to be higher than the Percy PSci 5.5 in its own detector, just because it's so much brighter. And so there are kind of like other situations like that where it gets a bit messy. So yeah, I mean, that getting around that problem that you're describing, it seems like that's kind of, it's almost more like a mathematical issue, because you're like, it doesn't like the detector being at a certain level. And so yeah, taking the voltage down in the non-used detectors just to get past everything, that seems fine to me. Like I said, like you would, the other option is you just delete those detectors from the thing, right, in Devo. Like then you're not detecting them, then there's no error. So it's like, well, I mean, I would probably rather keep them and just have changed the voltages, just because the extra info is just, it can be helpful for troubleshooting and stuff. So
yeah,
to me that sounds reasonable.
Yeah, sorry, David, go ahead.
Sorry, Eric, can you quickly just set those voltages for those channels you're not using, say using the application settings and the crosshairs? Do you know?
We
get them roughly, because I find it's one of the things, especially with people doing semi-high dimensional panels, is your empty channels, set your voltages on them properly and collect that data, because when the supervisor comes along and they want to add another marker in, you've got all that spreading error info there ready to go, and that will help you make the impossible decision for them on where to throw a marker type thing. I always find that interesting, useful. So, if there's an easy way you can just, open up your application settings and really roughly set those voltages on those crosshairs, that should give you a decent idea. They're not perfect, because some of the violet ones end up being much higher than they need to be, just because of the way the CST beads work in terms compared to what the voltage needs to be compared to a biological sample. But yeah, it might get you around that problem, and keep some of that info in that respect.
Cool. The thing is, we don't try and encourage deleting of channels, although some researchers, especially for the analyzers, they sort of tend to do, because the data is smaller in terms of maintenance, in hard drives and things like that. But the main reason is because we've seen before where a researcher recorded data, they couldn't see what they want to see, especially in an R660 channel.
They've used the wrong fluorophore on the antibody, haven't they?
No, they used the correct antibody, correct fluorophore.
Oh, really?
They were looking at the wrong channel. So they didn't realize that 660 and 690 is far enough. They messed up one of it. Okay, so we went through and we're like, do you use the correct channel? Not sure. So with the data, we can switch it around, and then they see that the separation and the proper population out there. So that's a balance. There's the researchers who like to do that, and then sometimes what happens is they record the whole thing, then they come around and say, hey, I duplicated this channel, I want to add a new channel because I've changed my panel a little bit. I want to add a channel in, and like, how do you do that without having to redo the whole thing? I'm like, sorry, man.
Yeah, that's what I mean, it's funny, like, it's stuff like that actually made like doing spectral work just much less of a headache for me, because I guess like, it doesn't really matter what the channel is. Actually, well, I mean, one thing is it actually made that troubleshooting easier, because I remember someone gave me a tube of what said PSI5, and I looked at it and I was like, dude, this is not PSI5. And like, I mean, you can tell on a conventional, I was like, nothing stops you from doing it on a conventional system, but just having the curves, it makes it so front and center, and you're like,
yeah,
the curve's wrong.
It just lets you show them, rather than, you got that sort of question in your head when you got one of those PE tandems that sort of is shifting down. Oh, is it really? Yeah. Whereas, when you see a spectra of 5 lasers, it's you're happy to go to court on that one. So
with some cytometers, though, the size of the file that you might want to, the number of parameters that you choose to collect on any particular assay will impact upon the maximum size of the file that could be remembered. So if you're working on something that you want to collect 10 or 20 million events on, if you can, keep the number of parameters down, you might have a chance of collecting it all in one file.
Yeah, that's interesting.
It's true. It works on the Navios is very sensitive to that. I think the BD instruments are less so. I don't know about the SciTech, but I imagine it wouldn't be so affected, given that it's probably going to collect at least 25 parameters with every test anyway.
Yeah, that is interesting. It's pretty rare that I'm trying to like record like 20 million cells or something, but like I did a bunch of bone marrow stem cell stuff like this where like I really had to go for it, and it was
yes. We're doing this now with minimal residual disease.
Of course, right. Yeah,
I try not to let users collect in Diva over 2.5 million, because I've had people that just doesn't render that, and then it just so just collect multiple files and amend them in Flowjo.
Yes,
I had one. I've got a scoot because I've got to go and buy single serve cutlery and stuff for tomorrow's watch party.
That's awesome.
I had one little troubling question that I had, and I don't know if it's ever been solved, but it's compensating in Flowjo. Can you compensate? Do you guys know how to compensate into empty channels? So say you collect, say you collect, the classic one was when we did our spreading error analysis on the Symphony, the UV 450/50 channel, which is sort of your FVS 440 UV. We didn't have a dye in that channel, so it's an empty channel. So we can't look at the spreading error of all our dyes into that channel because it's been taken off Diva, and I did try and So do you know, is there any trick you can do to make that work, or you're just
in Flowjo, well, so I mean, if it's, say, like, in Diva the detector's been deleted, then like that won't be in the file, which is unfortunate. But in Flowjo, yeah, you're right. It's like it only lets you do channels for which
you have a dye. You have a dye in, yeah.
I mean, so there is a workaround, and it's essentially a hack, because you can make it. You can, like, say, make a default comp matrix in Flowjo, and like you can edit those matrices as like
just do it manually.
Yeah, I mean, it's like I used to do it. There's a in my mind, I can just go and do it like now, but I can't quite explain exactly how I do it. So I'm gonna
I might pick your head out for that, because
that
really, you got your normal, your Diva associated matrix, but if you've got rid of that, you can create another matrix using the channels that have colors. But if you have something that you don't have a positive in, unless you put I can't even think how you'd even fake one, really. But
well, I mean, the matrix you end up with, if I can show this, so I mean, like, if you make a matrix, you end up with like you can export it as like a CSV file, and it just looks like like this. And I think, like, because I guess the naming and stuff is fairly formulaic for detector assignment, stain name, parameter assignment, stain assignment. I'm pretty sure you can just like force it to get like a.
Okay, so you just put a column in there, give it the same name as the detector, and then you import that into Flowjo, and then you'll have that column.
But it won't have the contribution into it. How the heck did I get around this before? Because I had to do this.
No, well, you won't.
Exactly.
You don't need it. You don't have a contribution because you can't. Flowjo hasn't calculated. But the problem is you can't even manually tweak it, because if you create a matrix in Flowjo, it doesn't let you create a matrix without a channel with a dye in it. So and you can't add that in. So maybe that's there. If you've got something that you don't have a positive in, that it can't compensate, then you're not going to be able to have a matrix even with that empty column.
Yeah.
So I'm wondering if what you were just doing then, if exported that as a CSV, added a column, and then you brought it back in, whether it would sit in your matrices just as a matrix, but it'd have that extra column that you could go and throw numbers in.
I mean, that one you would have to adjust manually, I guess. That sounds like a huge headache. I mean, so yes, that would work, I think. But I'm trying to, oh man, this is great. I'm now trying to think of how to do this the other way around. Like, can you just create Because like Diva does it, it'll just compensate it out of empty channels.
Diva,
Like,
yeah, you can
great.
have 20 empty. You can have, as long as you got 2 colors in Diva, you can create a comp matrix, and the other 28 are empty. But every die comped into those is comped against those empty channels properly. Whereas in Flojo, if you create a matrix in Flojo, you can't create something that doesn't have a die in it. You need a die in there. And it's just been something that on 4 or 5 occasions has just made me go and check the website and see if they've done something to improve.
Oh, actually, you know what? There is a way to do it. If you like, you can assign just like a sample as the positive control for that color. So I mean, let's say I didn't have anything in Fitzy. I could just assign a color there. I guess it would have to have a positive of some kind, but like, because I mean, what that's going to calculate is just the contribution of, you know, that to everything else. And so I can say, okay, well, Fitzy is actually contributing 0 across its row because it doesn't have any color, and then just keep the column info. That would actually work, because like I guess it would have to be stained with something. So maybe not unstained, but oh no, I guess you just pick the top and the bottom half of the unstained population would probably work. But like that actually in theory would let you do it, because it'll like basically that row for Fitzy's contribution to everything, you just turn back to 0, and then you'll have a Fitzy column, which will be only the contribution of everything else into the Fitzy detector. So that would work.
You try that. Can you quickly try that?
Well, yeah. So
because I've tried putting an unstained in there and just putting 2 arbitrary markers, and it didn't work.
Damn.
So
do I even have something in here called bone marrow unstained? Controls unstained. Oh, it's that one. Okay. Yeah, let's give this a shot. I'm really curious now. So
I am.
Yeah, let's go. Unstained control. That'll do. Oh gosh, let's see if that does anything. Matrix. Yeah, so it's got the column, and then those I can just set to, it's actually most of them already 0, but there you go. Because those could all be 0 because it's not a relevant contribution.
Not going anywhere.
But the column should be accurate.
So have you got a Fitzy? Yeah, have you got a column that's showing the comp of all the dies into Fitzy?
Well, yeah, it should be this first
That
one, but that doesn't look right. Let me have a quick little check, make sure I haven't done something bad here. I realize one of the downsides of like setting up things like this is like I mess around with it so much that when I come back to do the live demo, it's sort of like a complete catastrophe, and it's like, well, I should probably do this differently. Oh, no, sorry. All right. Here it is. I'm dead. Zombie, Fitzy. No, sorry, that is an Fmo. It's not going to help at all.
Well, at least you got the channel there. You can.
I think that value is just like an error, because I think in this case I don't have much live dead stain.
It's probably because where you put the negative and the positive on the Fitzy, it's probably confused.
Well, because this one, I mean, regardless of where I've set the gates, like it only contributes to the row, not to the column. So this I assume, like some of these other values are unexpectedly high. So I'm just going to go ahead and assume that the zombie is messed up. Like it should not be that high in the BB510 channel. So I'm going to assume there's something wrong with my live dead in this case, but yeah, the rest of that column looks good. So
if you go to your compensation control live dead and just look at that on the N by N, what does that look like?
Oh, yeah. That sort of makes sense. What does that mean? Yeah, it's definitely being overdone in a couple of places where it shouldn't be. That's a bit weird.
Maybe it may have moved the gates down.
Yeah. It might have.
That matrix, yeah.
As I didn't check anything else. I just kind of ran a fresh one, so maybe it screwed it up. Either way, I'm pretty sure that works.
Okay, cool.
So,
yeah, no, they'll try that. So cool. Anyway, Hooroo, everyone. Thank you very much, Thomas. Really good talk.
Cool.
Thanks,
Thanks for
everyone.
coming.
I've got it good as well. Take care. Catch you guys.
See you later.
Bye.
All right, I'll probably close it off now. Bye, everybody.